Hello, and welcome to Space Historians. I am truly glad you have joined me tonight, ready to slow down, breathe deeply, and let your thoughts drift weightlessly beyond our little blue world. Tonight, we are going to explore one of the simplest questions a human being can ask when looking up at the night sky, and yet it opens into something so vast that even after centuries of trying, we still cannot answer it with perfect certainty. How many stars are in our galaxy? It sounds like something you could count, like apples in a basket or birds in a tree. But the moment you try, the moment you truly try to grasp what that question means, the ground shifts beneath you. Because the Milky Way is not a basket, it is an ocean, and the stars are not apples. They are grains of sand scattered across a beach so large that you could spend 1,000 lifetimes walking it and never reach the end. Before we begin this journey together, I would love to know, where are you listening from tonight? And what time is it where you are? Perhaps you are in a city where light pollution hides most of the stars, or maybe you are somewhere dark enough to see the Milky Way stretching overhead like a river of light. Either way, know that above you right now, whether you can see them or not, there are hundreds of billions of stars sharing this galaxy with you. If you enjoy these quiet journeys through time and space, a like and a subscribe help keep this channel orbiting steadily. And for those who have already joined this growing constellation of listeners, thank you. You are part of this voyage, part of this shared wonder. Each episode here is not just about numbers or facts. It is about the stories behind them, the centuries of human curiosity that brought us to where we are today, the astronomers who spent their entire lives trying to count something that cannot truly be counted, and the quiet beauty of accepting that some questions lead not to answers, but to deeper mysteries. So tonight, as your eyes grow heavy and your breathing slows, imagine yourself floating gently above Earth, drifting up through the atmosphere until you can see the curve of the planet below, and then higher still, past the moon, past the orbit of satellites, until you are floating in the great disk of the Milky Way itself, surrounded on all sides by stars. How many are there? That is what we will explore tonight. Not with perfect precision, because that is impossible, but with wonder, with patience, and with the understanding that sometimes the most beautiful questions are the ones we can never fully answer. If you gently press the notification bell, you will always know when the next journey begins. But for now, you do not need to do anything but listen, breathe, and drift. Let us travel together into the heart of a question that has haunted humanity for thousands of years. A question that sounds so simple, but opens into infinity. Welcome to the quiet side of the cosmos. There is a moment that happens to almost everyone who truly thinks about the night sky for the first time. You step outside on a clear evening, far from the glow of cities, and you look up. The stars appear scattered across the darkness like diamonds on velvet, and your first instinct is to try to count them. 1, 2, 3, you begin. But soon the numbers blur. They multiply faster than you can track them, and somewhere around a few dozen, you give up, not because you are lazy, but because the task itself reveals its impossibility. That is the moment when you realize that counting stars is not like counting anything else. If you could somehow continue, if your eyes were perfect and your patience infinite, you might count a few thousand stars visible to the naked eye on a truly dark night. But here is the truth that stops you cold. Those few thousand stars are not even a fraction of what is really there. They are not even a percentage. They are barely a whisper of the hundreds of billions that fill the day. Milky Way, most of them hidden by distance, by dust, by the simple fact that they are too faint for human eyes to register. The question of how many stars are in our galaxy sounds straightforward, like asking how many books are in a library or how many people live in a city. But the Milky Way is not a library you can walk through shelf by shelf. It is not a city you can census door by door. It is a spiral of light and matter stretching 100,000 light years from edge to edge, and we are trapped inside it, unable to step back and see the whole picture. Imagine trying to count every tree in a forest while standing in the middle of it. The nearby trees are visible, but the distant ones blend together into a haze. Some are hidden behind hills, others are obscured by fog. You cannot fly above the forest to see its true size. You cannot walk to its edges because they are too far away. All you can do is sample a small area, measure what you find, and try to extrapolate outward, hoping your guesses are close to the truth. That is exactly what astronomers have been doing for more than a century. And what they have found is both humbling and astonishing. The current best estimates suggest that the Milky Way contains somewhere between 100 billion and 400 billion stars. That range alone should tell you something. The uncertainty spans hundreds of billions of stars, more than the number of humans who have ever lived on Earth, more than the number of grains of sand on many beaches, more than most minds can truly comprehend. 100 billion stars. Say it slowly. 100 billion. If you started counting right now, 1 star per second, without stopping to eat or sleep or breathe, it would take you more than 3,000 years to reach 100 billion. And that is just the low end of the estimate. If the true number is closer to 400 billion, you would need over 12,000 years of constant counting. But here is what makes the question even more impossible. What exactly are we counting? Are we counting only the stars that shine brightly enough to be detected by our telescopes? Or do we include the countless red dwarfs, tiny stars so dim they are almost invisible even with powerful instruments? Do we count brown dwarfs, those failed stars that never quite ignited full fusion in their cores? Do we count the dead remnants, the white dwarfs and neutron stars that no longer burn but still exist? Every definition changes the number. Every method of measurement introduces uncertainty, and every new survey reveals populations of stars we did not know existed. The Milky Way is not just full of stars, it is full of hidden stars. Stars obscured by thick clouds of interstellar dust. Stars so faint they barely register on our most sensitive detectors. Stars in the crowded central bulge where thousands are packed so tightly together that separating them becomes nearly impossible. Stars in the outer halo, drifting, alone in the dark, far from the bright disk we think of as the galaxy. Most of the stars you see in the night sky are not typical. They are the exceptions, the rare giants and supergiants that shine brilliantly enough to catch your eye across thousands of light years. The typical star in the Milky Way is a red dwarf, a small, cool, faint star that you could never see without a telescope, even if it were relatively close by. And these red dwarfs, these invisible majority, make up perhaps 70 or 80% of all the stars in the galaxy. So when you ask how many stars are in the Milky Way, you are really asking how many invisible things exist in a place you cannot fully see, using methods that rely on assumptions and extrapolations, measured by instruments that can only detect a fraction of what is there. It is an impossible question, but it is also an irresistible one, because despite the uncertainties, despite the vast scales and the hidden populations, astronomers have managed to arrive at an answer. Not a perfect answer, not a final answer, but an answer good enough to give us a sense of scale, good enough to make us feel hundreds of billions of stars. That is what shares this galaxy with us. Hundreds of billions of suns, each one burning with its own light, each one following the same laws of physics that govern our own sun. Each one a potential center for planets, for worlds, for for possibilities we cannot yet imagine. The number is so large it loses meaning, but that is part of its power, because when you try to hold that number in your mind, when you try to picture hundreds of billions of stars scattered through a disk of space, 100,000 light years across, something shifts. The ordinary concerns of daily life seem smaller. The universe feels larger, and you begin to understand, in a way that goes beyond words, just how immense and how crowded and how astonishingly full of light our galaxy truly is. This is the impossible beginning, a question that sounds simple but opens into infinity, a number that is both known and unknowable, a census of stars that we will never complete but cannot stop trying to conduct. And tonight, as we drift through this question together, we will trace the path that led us here. We will follow the astronomers who first tried to count the stars, the methods they invented, the discoveries they made, and the mysteries they uncovered. We will learn why the answer is so uncertain, why it matters so much, and what it tells us about our place in the cosmos. But first, we must accept the impossible beginning. We must accept that the question itself is almost unanswerable. And we must find comfort in the fact that even without perfect certainty, even without exact numbers, we know enough to understand that we are surrounded by more stars than we can count, more light than we can see, more companionship in the darkness than we ever could have imagined. The Milky Way holds hundreds of billions of stars, and we are floating quietly among them, one small world orbiting one ordinary star, asking questions that stretch toward infinity. To understand how we arrived at the question of how many stars fill our galaxy, we need to step back in time, back to when the very idea of a galaxy did not exist, when the Milky Way was just a mysterious band of light across the night sky, and when counting stars seemed like it might actually be possible. For most of human history, people looked up at the heavens and saw what appeared to be a manageable number of stars, a few thousand, perhaps, scattered across the dome of the sky. They named them, grouped them into constellations, wove them into myths and stories. The brightest ones became navigational markers, seasonal indicators, gods, and heroes frozen in light. The sky felt knowable, mappable, countable, but there was always that strange, pale band stretching from horizon to horizon on clear nights. The Greeks called it the Milky Circle. The Romans named it the Milky Way, believing it to be a river of spilled milk from the goddess Juno. Other cultures saw it as a path for souls, a bridge between worlds, a celestial river where gods travelled. No one knew what it truly was. Some philosophers speculated it might be distant stars packed so closely together their light blended into a glow. Others thought it was some kind of celestial fog or fire. The mystery persisted for thousands of years. Ancient astronomers catalogued the visible stars, counting them meticulously. Hipparchus, working in the 2nd century before the Common Era, compiled a catalogue of around 850 stars, noting their positions and brightness. Ptolemy expanded this work, and his catalogue remained the standard for over 1,000 years. These early catalogues were triumphs of patience and observation, but they only accounted for what the naked eye could see. The limitation was fundamental. Human vision is remarkable in many ways, but it has boundaries. The faintest stars visible to the unaided eye have a magnitude of about 6, a measurement of brightness where lower numbers mean brighter objects. Beyond that threshold, stars simply vanish into darkness, not because they do not exist, but because our eyes cannot detect them. For millennia, that was the extent of human knowledge. A few thousand visible stars, a mysterious glowing band called the Milky Way, and no way to see deeper into the darkness beyond. Everything changed in 1609 when Galileo Galilei turned his newly constructed telescope toward the heavens. It was a simple instrument by modern standards, magnifying objects only about 20 times, but it was enough to revolutionize our understanding of the cosmos. When Galileo pointed his telescope at the Milky Way, he saw something that no human had ever seen before. The pale, glowing band resolved into countless individual stars, packed so densely that from a distance they appeared to merge into a continuous light. In his book Sidereus Nuncius, The Starry Messenger, published in 1610, Galileo described what he saw. He wrote that the Milky Way was nothing but a congeries of innumerable stars distributed in clusters. The mystery was solved. The Milky Way was not fog or fire. It was stars. More stars than anyone had imagined, too faint individually to be seen with the naked eye, but collectively creating that familiar glow. That discovery changed everything. It meant the universe contained far more stars than the few thousand visible to human eyes. But it also raised a new and more daunting question. If the Milky Way was made of stars, how many were there? Galileo could not answer that question. His telescope revealed more stars, but it also revealed that the more deeply you looked, the more stars appeared. It was like peeling back layers of an onion, only to find more layers beneath. Every improvement in telescope technology revealed fainter stars, and every survey of the sky uncovered populations that had been invisible before. As telescopes improved through the 17th and 18th centuries, astronomers began attempting systematic surveys of the sky. William Herschel, working in the late 1700s, built some of the largest telescopes of his era and used them to count stars in different directions. His method was straightforward but laborious. He would point his telescope at a region of sky, count the stars he could see, and then repeat the process in other directions. By comparing the density of stars in different parts of the sky, he hoped to map the shape and extent of what he called the starry system. Herschel's work was pioneering, but it was also limited by the technology of his time and by his position inside the system he was trying to map. He assumed, reasonably given the evidence available, that he could see to the edges of the starry system in most directions. This led him to conclude that the Sun was near the center of a disc-shaped collection of stars. He estimated that this disk might contain a few million stars, a number that seemed vast at the time, but would soon prove to be a dramatic underestimate. What Herschel could not account for was the dust. Interstellar space is not empty. It is filled with clouds of gas and microscopic grains of dust, particles so small that individually they are insignificant, but collectively they can block and scatter light across vast distances. These dust clouds lie primarily in the plane of the Milky Way, obscuring our view of the more distant stars. When Herschel looked in certain directions, he was not seeing to the edge of the starry system. He was seeing only as far as the dust would allow. This problem would plague astronomers for more than a century. Without a way to see through the dust, without a way to measure distances accurately, and without an understanding of the true scale of Grey Esther, the Milky Way, estimates of the number of stars remained wildly uncertain. The setting for our question began to shift dramatically in the early 20th century. New tools emerged. Photography allowed astronomers to record the sky with far greater sensitivity than the human eye, capturing faint stars that would never register in a visual observation. Spectroscopy, the study of light broken into its component wavelengths, allowed astronomers to determine not just where stars were, but what they were made of, how hot they burned, and how far away they might be. But perhaps the most important breakthrough came from understanding distance. For most of history, stars had been points of light with no known separation. Some were brighter, some dimmer. But whether that was because they were intrinsically different or simply at different distances was impossible to say. Without distance measurements, there could be no true map of the Milky Way, and without a map, there could be no accurate count of its stars. The breakthrough came from a type of star called a Cepheid variable. These stars pulse in brightness with regular periods, and in the early 1900s, astronomer Henrietta Swan-Leavitt discovered that the period of a Cepheid's pulsation is directly related to its intrinsic brightness. This meant that by measuring how quickly a Cepheid pulsed, you could determine how bright it truly was, and by comparing that intrinsic brightness to how bright it appeared from Earth, you could calculate its distance. This was revolutionary. Cepheids became cosmic distance markers, standard candles that could be used to measure the scale of the universe. And when astronomers began finding Cepheids in what were then called spiral nebulae, they discovered something shocking. These nebulae were not nearby clouds of gas within the Milky Way. They were entire galaxies, millions of light years away, each one containing billions of stars. In 1924, Edwin Hubble used Cepheid variables to measure the distance to the Andromeda Nebula, proving conclusively that it was a separate galaxy far beyond the boundaries of the Milky Way. The universe, it turned out, was far larger than anyone had imagined, and if Andromeda was a galaxy, then the Milky Way must be a galaxy too. A vast system of stars stretching across tens of thousands of light years. This realization redefined the question. The setting was no longer a small, countable starry system centered on the Sun. It was a massive spiral galaxy containing incomprehensible numbers of stars, most of them too distant or too faint to be seen, many of them hidden behind veils of dust, all of them orbiting a common center over the course of hundreds of millions of years. The setting was vast, the setting was dynamic, and the setting was only beginning to reveal itself. By the mid-20th century, astronomers had a rough sense of the Milky Way's structure. It was a disk about 100,000 light years across, with spiral arms winding outward from a central bulge. Our Sun sat about 2/3 of the way out from the center, in one of those spiral arms. The galaxy was not infinite, but it was so large that light took 100,000 years to cross from one edge to the other. The setting also included time. Stars were not eternal fixtures. They were born in clouds of gas and dust, lived for millions or billions of years depending on their mass, and then died, sometimes quietly, sometimes in spectacular explosions. The Milky Way was not a static collection of stars. It was a living, evolving system, constantly forming new stars even as old ones faded away. And throughout all of this, the central question persisted. If the Milky Way is this large, if it contains spiral arms and a central bulge and a halo of ancient clusters, if it stretches across such immense distances and hides so much behind dust, then how many stars does it actually contain? The setting was established. The stage was set. The question was clear. But the answer remained elusive, waiting for generations of astronomers to develop the methods, the instruments, and the patience to pursue it. From ancient catalogues of a few hundred stars to Galileo's revelation of countless more, from Herschel's early maps to Hubble's proof of other galaxies, the journey had taken humanity from thinking we could count every star to realizing we would have to estimate billions upon billions of them. The setting was no longer a simple sky above a simple Earth. It was a galaxy, our galaxy, vast and complex and full of hidden light. And we were inside it, looking out, trying to understand just how many companions we had in the darkness. There is something deeply human about the moment when a simple observation transforms into a profound mystery, when what you thought you understood suddenly reveals itself to be far stranger, far larger, far more complex than you ever imagined. For astronomers trying to understand the Milky Way, that moment came not from a single discovery, but from a gradual accumulation of observations that kept pushing the boundaries of what seemed possible. The spark of mystery began with a simple fact. The more carefully astronomers looked at the sky, the more stars they found. Every increase in telescope size revealed fainter stars. Every improvement in photographic emulsions captured objects too dim to see visually. Every new survey of the sky uncovered populations that had been invisible before. The universe was not revealing its full inventory easily. It was hiding most of its stars behind barriers of distance, dust, and faintness. In the early 20th century, as telescopes grew larger and techniques improved, astronomers began attempting systematic surveys of the Milky Way. They photographed large sections of the sky, counted the stars in each photograph, and tried to build a census. But the results were puzzling. Different regions of the sky showed wildly different star densities. Looking toward the constellation Sagittarius, where the center of the Milky Way lies, the star fields were incredibly rich, packed with more stars than could be easily counted. Looking perpendicular to the plane of the Milky Way, toward the galactic poles, the star density dropped dramatically. This variation was expected to some degree. If the Milky Way was a disc-shaped system, then looking along the disk should reveal more stars than looking perpendicular to it, just as looking down the length of a forest reveals more trees than looking at it from the side. But the variation was more extreme than the simple disk model predicted. And more troubling, there were dark patches, regions where stars seemed to be missing entirely, as if holes had been carved into the fabric of the Milky Way. The mystery deepened when astronomers realized these dark patches were not holes at all. They were dust clouds, vast accumulations of tiny particles that blocked starlight. Discovery of interstellar dust was itself a revelation. Space was not empty. It was filled with material that could obscure, scatter, and absorb light, making distant stars invisible or appearing much fainter than they truly were. This meant that many of the early estimates of the Milky Way's size and population were wrong. Astronomers had been seeing only as far as the dust allowed, mistaking limited visibility for the actual edge of the galaxy. It was like trying to map an entire city while standing in heavy fog. The nearest buildings were visible, but everything beyond a certain distance vanished into grey obscurity, and there was no way to know how far the city actually extended. One of the astronomers who grappled with this mystery was Harlow Shapley. In the 1910s, Shapley studied globular clusters, dense spherical collections of hundreds of thousands of ancient stars that orbit the Milky Way in a halo. By measuring the distances to these clusters using Cepheid variables, he was able to map their distribution in 3 dimensions. What he found was startling. The globular clusters were not centered on the Sun. They were centered on a point about 26,000 light-years away in the direction of Sagittarius. This could only mean one thing. The Sun was not at the center of the Milky Way. We were off to the side, orbiting a distant center that we could barely see through the intervening dust. Shapley's work redefined our understanding of the galaxy's structure and our place within it. We were not special. We were not central. We were residents of the suburbs, orbiting quietly in one of the spiral arms, far from the crowded core. But Shapley's work also revealed just how large the Milky Way was. His estimates suggested the galaxy might be 300,000 light-years across, far larger than previous estimates. Though later refinements would reduce that number to about 100,000 light-years, the point was clear. The Milky Way was vast, far vaster than anyone had realized. This discovery sparked a new mystery. If the galaxy was this large, how many stars did it contain? Early estimates based on limited surveys suggested millions of stars. But those estimates were clearly too low. They did not account for the faint stars, the hidden stars, the countless red dwarfs too dim to detect with the instruments of the time. They did not account for the stars hidden behind dust, the stars in the crowded central bulge, the stars in the halo drifting in the darkness beyond the disk. The spark of mystery was the realization that the Milky Way was not just big, it was hiding most of itself. Every new method of observation revealed something unexpected. Infrared observations, which could pierce through dust, showed stars in regions that appeared dark in visible light. Radio observations revealed hydrogen gas spread throughout the galaxy, tracing the spiral arms and hinting at regions of ongoing star formation. X-ray observations found compact objects like neutron stars and black holes, remnants of stars that had died long ago. Each wavelength of light told a different story. Each survey revealed a different population of stars, and each discovery made it clear that counting the stars of the Milky Way would be far more difficult than anyone had anticipated. The mystery was not just about numbers, it was about understanding what kinds of stars existed and in what proportions. The brightest stars, the ones that dominated the night sky, were actually quite rare. Most stars were much smaller and dimmer, so faint they could barely be detected even in nearby space. These red dwarfs, as they came to be called, might make up the majority of the galaxy's stars, but they contributed very little to its total light. Counting them would require surveys of unprecedented sensitivity, capable of detecting objects thousands or millions of times fainter than what the naked eye could see. Another layer of mystery came from stellar remnants. When stars die, they leave behind white dwarfs, neutron stars, or black holes. These objects are incredibly faint or completely dark, contributing to the galaxy's mass but not to its visible light. Should they be counted among the stars? If so, the total number would rise, but detecting them would be almost impossible. And then there were the brown dwarfs, objects too small to ignite full hydrogen fusion in their cores. They are not quite stars, not quite planets, occupying a grey area between the two. Early surveys missed them entirely because they are so faint, glowing mainly in infrared wavelengths. But as detection methods improved, astronomers began finding brown dwarfs in surprising numbers, suggesting there might be billions of them scattered throughout the galaxy. Did they count as stars? The answer depended on definitions, and definitions changed the total dramatically. The spark of mystery was this growing awareness that the question of how many stars are in the Milky Way was not straightforward. It was a question tangled up with issues of detection, definition, and distribution. Every attempt to answer it revealed new complications, new populations, new uncertainties. But the mystery was also deeply compelling, because even though the exact number remained elusive, the scale was becoming clear. Astronomers might not know whether the galaxy contained 100 billion stars or 400 billion, but they knew it was in that range. They knew the Milky Way was not a small collection of a few million visible stars. It was a vast system containing hundreds of billions of suns, most of them invisible to human eyes, scattered across a disk so wide that light took 100,000 years to cross it. The spark of mystery ignited a pursuit that would occupy astronomers for generations. It drove the development of new telescopes, new surveys, new techniques for measuring distances and counting faint objects. It pushed observers to catalogue millions of stars, to peer deeper into the darkness, to account for populations that previous generations had never known existed. And at the heart of the mystery was a simple, profound realization. We live inside something vast. We are surrounded by more stars than we can count, embedded in a structure so large that we cannot see its entirety. Part of a system that has existed for billions of years, and will continue long after we are gone. The discovery was not a single moment, but a gradual unveiling. Each observation added a piece to the puzzle. Each new survey expanded the known population. Each technological advance revealed hidden multitudes. The spark of mystery was the recognition that the Milky Way was not going to give up its secrets easily. It would require patience, ingenuity, and humility. It would require accepting uncertainty while still striving for understanding. And so the mystery endured, not as a failure of science, but as an invitation. An invitation to look deeper, to measure more carefully, to account for the invisible as well as the visible. An invitation to grapple with scales that stretched beyond human comprehension and to find meaning in the enormity. The spark had been struck. The mystery was alive. And astronomers would spend the next century chasing it into the farthest reaches of the galaxy, counting stars one survey at a time, building toward an answer that would never be perfect, but would be close enough to glimpse the true nature of our cosmic home. When astronomers first began to grasp the true scale of the Milky Way, when they realized the galaxy was not thousands of stars but potentially billions, the initial response was a mixture of awe and disbelief. It was one thing to make measurements, to run calculations, to publish papers with estimates. It was another thing entirely to sit with those numbers and try to comprehend what they meant. Billions of stars. The very phrase seemed absurd. How could, to anyone, verify such a claim? How could anyone be certain they were not making a massive error, overestimating by orders of magnitude? The history of astronomy was full of mistakes, of assumptions that turned out to be wrong, of measurements that had to be revised. Surely this was another case of reaching too far, of letting imagination run ahead of evidence. But the evidence kept accumulating, and the more carefully astronomers looked, the more they realized the early estimates might actually be too low, not too high. The disbelief came in waves. First, there was the realization that the Milky Way was much larger than previously thought. Harlow Shapley's work on globular clusters suggested a galaxy 300,000 light-years across, though that estimate was later revised downward. Even at 100,000 light-years, the scale was staggering. It meant the galaxy was so large that light, travelling at 300,000 kilometers per second, took 100,000 years to cross from edge to edge. If the galaxy was that large, and if it was filled with stars at even a modest density, the total number quickly climbed into the billions. Simple arithmetic made it clear. If you knew the volume of the galaxy and you knew the average density of stars in a given region, you could multiply and arrive at a total. The problem was that neither the volume nor the density was known with any certainty. The galaxy's boundaries were fuzzy. The density varied dramatically from place to place, and vast regions remained unmapped, hidden behind dust, or simply too faint to observe. Early estimates from the 1920s and 30s suggested the Milky Way might contain 10 billion stars, perhaps as many as 30 billion. These were already numbers far beyond human intuition. 30 billion seconds is nearly 1,000 years. 30 billion grains of rice would fill a large warehouse. 30 billion stars scattered across a disk. 100,000 light, years wide, was almost incomprehensible. But even these estimates were quickly challenged. As surveys extended to fainter magnitudes, as infrared observations revealed populations hidden by dust, as understanding of stellar types improved, it became clear that the vast majority of stars were not the bright, visible ones that dominated the sky. Most stars were small, cool, red dwarfs, so faint they could barely be detected even at relatively close distances. If red dwarfs made up 70 or 80% of all stars, as some studies suggested, then the total count had to be revised upward dramatically. By mid-century, estimates had climbed to 100 billion stars or more. 100 billion. The number was so large it defied meaningful comparison. It was roughly the number of stars in many other galaxies. It was orders of magnitude greater than the number of humans who had ever lived on Earth. It was a number that, when spoken aloud, sounded more like a mistake than a two measurement. And yet, the evidence supported it. Large-scale surveys, statistical analyses of stellar populations, measurements of the galaxy's total mass, all pointed toward a number in the hundreds of billions. The disbelief began to give way to awe at the sheer abundance of light. If every star was a sun, and many were far more luminous than our own, then the Milky Way contained an almost unimaginable amount of energy. Every second, hundreds of billions of stars were burning, fusing hydrogen into helium, releasing radiation that traveled outward into space. The collective light of all those stars was what made the Milky Way visible from other galaxies, a glowing spiral against the darkness. Awe at the diversity. Those billions of stars were not all the same. Some were massive blue giants, burning hot and bright, living fast and dying young. Others were small red dwarfs, glowing faintly but steadily for trillions of years. Some were ancient, formed when the galaxy was young. Others were newborn, just igniting in clouds of gas and dust. Some were alone. Others orbited companions in binary or multiple systems. Each one was unique, following its own path through the galaxy. At the implications. If there were hundreds of billions of stars, and if even a fraction of them had planets, then the number of worlds in the galaxy could be staggering. Estimates varied, but if even 1 in 10 stars had a planetary system, that meant tens of billions of planets. If even 1 in 100 of those planets was in a habitable zone, where liquid water could exist, that meant hundreds of millions of potentially habitable worlds. The possibility of life elsewhere suddenly seemed not just plausible but likely. With hundreds of billions of stars and potentially billions of planets, the idea that Earth was the only world with life began to seem not just pessimistic, but statistically absurd. The Milky Way was not a lonely place. It was crowded with possibilities, but the awe was tempered by uncertainty. Even as estimates climbed into the hundreds of billions, the range of possible values remained wide. Was the true number 100 billion, 200 billion, 400 billion? Each estimate depended on assumptions. How many faint stars were there per visible star? How much mass was hidden in stellar remnants? How complete were the surveys? How accurate were the models? Every assumption introduced error, and the errors compounded. A small uncertainty in one parameter could lead to a large uncertainty in the final total. Astronomers spoke in ranges rather than precise figures, acknowledging that the exact number might forever remain elusive. There was also philosophical disbelief. Could humanity really claim to know how many stars filled the galaxy when we had only observed a tiny fraction of them directly? Most of the total was inferred, not measured. It was based on sampling and extrapolation, on models and assumptions. Informed by data, but never fully verified. Some scientists pushed back against the high estimates. They argued that the surveys were incomplete, that the models were oversimplified, that the uncertainties were being downplayed. They pointed to the difficulties of observing through dust, of detecting faint stars, of accounting for binary systems where multiple stars appeared as one. They cautioned against overconfidence, but the majority of astronomers accepted the emerging consensus. The Milky Way contained hundreds of billions of stars. The exact number might be uncertain, but the order of magnitude was clear. We were not living in a galaxy of millions of stars. we were living in a galaxy of hundreds of billions. The first response, that mixture of awe and disbelief, gradually settled into acceptance. The numbers were confirmed and reconfirmed by independent surveys. The methods were refined and improved. The uncertainties were acknowledged, but did not invalidate the central conclusion. What remained was the awe, the pure, overwhelming sense of wonder at realizing we live in a galaxy so vast, so full of light, so rich with stars that even our best efforts at counting barely scratch the surface. The disbelief faded, but the awe never did. Because even when you accept the numbers, even when you understand the methods and the evidence, the scale still defies intuition. Hundreds of billions of stars, each one a sun, each one potentially hosting worlds, all of them orbiting together in a great spiral dance that takes hundreds of millions of years to complete. The first response was awe and disbelief. But the lasting response, the one that endures even now, is simply awe. Awe at the abundance, awe at the complexity, awe at the realization that we are surrounded by more companions in the darkness than we could ever hope to count. Science thrives on precision. It demands measurements, data, repeatability. It builds theories on firm foundations of observation and experiment. But sometimes, science encounters questions where precision seems impossible, where every answer comes wrapped in caveats and uncertainties, where the very act of measurement reveals how little we can truly know. The question of how many stars are in the Milky Way is one of those questions. The contradiction at the heart of this mystery is simple yet profound. Science tells us we can measure and count anything if we have the right tools and methods. But the Milky Way is not a laboratory sample. It is not a controlled experiment. It is a vast, complex, dynamic system that we are trapped inside, unable to see from outside, unable to sample completely, unable to count directly. Every method developed to estimate the number of stars comes with limitations. Every measurement introduces uncertainty, and every attempt to reconcile the different estimates reveals contradictions that cannot be fully resolved. The first contradiction is observational. To count stars, you need to see to them. But most stars in the Milky Way are invisible. They are too faint, too distant, or too obscured by dust to be detected even with our most powerful telescopes. Visible light surveys capture only a fraction of the total population. Infrared surveys can see through dust, but have their own limitations in sensitivity and resolution. Radio observations reveal gas, but not individual stars. X-ray telescopes find compact objects, but miss ordinary stars entirely. Each wavelength tells part of the story, but no single method reveals everything. To get a complete picture, astronomers must combine data from multiple surveys across many wavelengths, each with its own biases and blind spots. The result is a composite image that is better than any single survey, but still incomplete. The second contradiction involves definition. What exactly counts as a star? The obvious answer is any object massive enough to sustain hydrogen fusion in its core. But where is the boundary? Brown dwarfs are not quite massive enough for full fusion, but do fuse deuterium briefly in their youth. Do they count? White dwarfs are stellar remnants, no longer fusing anything, but they are the corpses of former stars. Should they be included? Different studies make different choices, and those choices dramatically affect the final count. Including brown dwarfs might add tens or even hundreds of billions to the total. Excluding white dwarfs removes another significant population. The number depends not just on measurement but on semantics. The third contradiction is statistical. Astronomers cannot count stars individually across the entire galaxy. Instead, they sample small regions, measure the density of stars, and extrapolate to the whole. But the Milky Way is not uniform. The central bulge is densely packed with old stars. The spiral arms are rich in young, bright ones. The regions between arms are sparser. The halo contains globular clusters and scattered field stars. Each region has its own character, and each requires separate treatment. Extrapolating from one region to the entire galaxy is fraught with uncertainty. If your sample happens to fall in a dense region, you might overestimate the total. If it falls in a sparse region, you might underestimate. Astronomers try to account for this by sampling many regions and weighing the results, but the uncertainty never entirely disappears. The fourth contradiction involves time. The galaxy is not static. Stars are constantly being born in clouds of gas and dust. Others are dying, exploding as supernovae or fading into white dwarfs. The total number of stars changes over time, albeit slowly on human scales. When we ask how many stars are in the Milky Way, we are asking about a snapshot in time, a census of the present moment. But the galaxy's population 10 million years ago was different, and it will be different 10 million years from now. This temporal dimension adds another layer of uncertainty. Are we counting only currently active stars? Or do we include the remnants of stars that died long ago? What about protostars? Objects in the process of forming but not yet ignited? The answer depends on when and where you draw the line. The fifth contradiction is philosophical. Science seeks objective truths, facts independent of the observer. But the question of how many stars exist in the galaxy is inherently tied to our methods of observation and our definitions. In a sense, the number we arrive at is not purely objective. It is shaped by our instruments, our assumptions, our choices about what to count and how to count it. But it does mean there is no single, definitive answer that exists independently of the process we use to find it. The number we get is as much a product of our methods as it is a property of the galaxy itself. Despite these contradictions, science has not given up. Instead, astronomers have embraced uncertainty as part of the answer. They present results as ranges rather than exact figures. They acknowledge the limitations of their methods. They continually refine their estimates as new data becomes available. The current consensus is that the Milky Way contains somewhere between 100 billion and 400 billion stars. That range is wide, spanning hundreds of billions, but it represents our best understanding given the available evidence. It is both a triumph and a confession. A triumph because it narrows the possibilities from infinite to finite. A confession because it admits we cannot yet do better. The contradiction between science and mystery is not resolved. It is managed. Astronomers work within the constraints of their position inside the galaxy, their limited instruments, and their incomplete surveys. They develop clever methods to infer what cannot be directly observed. They build models to simulate populations they cannot fully measure. They compare independent estimates to check for consistency. And through all of this, they accept that the question may never have a perfectly precise answer. Not because science has failed, but because the question itself exceeds the limits of what direct measurement can achieve. We are asking about hundreds of billions of objects spread across 100,000 light years, most of them too faint to see, many of them hidden behind dust, all of them part of a system so vast we can only glimpse fragments of it at a time. The contradiction is that we can know enough to answer the question meaningfully, but not enough to answer it definitively. We can say with confidence that the number is in the hundreds of billions. We cannot say with confidence whether it is closer to 100 or 400 billion. Both numbers are supported by evidence. Both are consistent with observations. The difference lies in assumptions about populations we cannot fully observe. And so, the contradiction endures. Science tells us the Milky Way contains hundreds of billions of stars. Mystery reminds us that we will never count them all. We are left with a number that is both known and unknown, both measured and estimated, both precise in scale and uncertain in detail. Perhaps that is fitting. Perhaps the question of how many stars fill our galaxy is meant to remain partly mysterious, a reminder that even in an age of powerful telescopes and sophisticated models, the universe still holds truths that exceed our grasp. We can approach them. We can narrow the possibilities. We can arrive at reasonable estimates. But we cannot eliminate the mystery entirely. And maybe we should not want to. Because in that tension between knowing and not knowing, in that space where science meets mystery, we find something profound. We find humility in the face of vastness. We find wonder in the face of complexity. We find a question that keeps us reaching, keeps us exploring, keeps us striving to understand just a little bit more. The contradiction is not a weakness. It is part of the story. Science and mystery, precision and uncertainty, knowledge and wonder, all bound together in a question that will never be fully answered, but will always be worth asking. When faced with a question that cannot be answered through direct observation, when the object of study is too large and too complex to measure completely, scientists do what they have always done. They build theories. They develop methods. They propose approaches that might bridge the gap between the observable and the total, between the sample and the whole. And in doing so, they inevitably divide, each school of thought favoring different assumptions, different techniques, different paths toward an answer. The question of how many stars fill the Milky Way has generated numerous theories over the decades, each one reflecting a particular way of thinking about the problem, each one producing estimates that sometimes agree and sometimes conflict. These theories are not guesses. They are structured approaches grounded in observation and mathematics. But they rest on different foundations, and those foundations lead to different conclusions. One of the earliest and most straightforward theories was direct sampling. The idea was simple. Survey a representative section of the sky, count the stars within it, and multiply by the total area of the galaxy. If you counted 1,000 stars in a square degree of sky, and the galaxy covered a certain number of square degrees, you could calculate a total. It required only patient observation and basic arithmetic, but it was also deeply flawed. The Milky Way is not uniform. Sampling one region and extrapolating to the whole could produce wildly different results depending on where you looked. A survey directed toward the galactic center would yield a much higher star density than one aimed at the halo. A survey that happened to intersect a star cluster would overestimate the average density. And most critically, this method could only count visible stars, missing the vast majority that were too faint or too obscured to detect. As these limitations became clear, astronomers developed more sophisticated approaches. One was the luminosity function method. Instead of simply counting stars, this approach classified them by brightness, building a distribution that showed how many stars existed at each level of luminosity. By carefully studying nearby regions where even faint stars could be detected, astronomers could determine the shape of this luminosity function, the ratio of bright stars to dim ones. Then they could apply that ratio to the galaxy as a whole. This method acknowledged that most stars are faint, and that visible surveys capture only the bright minority. By accounting for the hidden population of red dwarfs and other low-luminosity objects, it produced much higher estimates than simple direct counts. The luminosity function approach suggested the Milky Way might contain not millions but billions of stars, with the majority being small, cool red dwarfs that contributed little to the galaxy's total light, but dominated the census by sheer numbers. Another theory focused on mass rather than light. Astronomers measured the total mass of the Milky Way by studying how stars and gas orbited the galactic center. The speed of these orbits depended on the gravitational pull, which in turn depended on the total mass enclosed within the orbit. By measuring velocities at different distances, they could build a rotation curve that revealed the galaxy's mass distribution. Once the total mass was known, or at least estimated, it could be divided by the average mass of a star to arrive at a number. The challenge was that the total mass included not just stars but gas, dust, and dark matter. Separating these components required careful modelling. The average stellar mass also introduced uncertainty. If you assumed most stars were sun-like, you would get one answer. If you assumed most were red dwarfs with much lower mass, the number of stars would be correspondingly higher. The mass-based approach consistently suggested that the Milky Way contained hundreds of billions of stars, but the exact number depended heavily on assumptions about dark matter and the distribution of stellar types. Different studies produced different estimates, sometimes varying by a factor of 2 or more. A third major theory involved comparing the Milky Way to other galaxies. By observing spiral galaxies similar to our own, astronomers could measure their total light output and estimate their stellar populations. These external galaxies offered a perspective we could never have from inside the Milky Way. They showed how spiral arms wound, how bulges formed, how the distribution of light correlated with the distribution of stars. By calibrating the relationship between light and stellar population in these external galaxies, astronomers could apply the same principles to the Milky Way. If a similar galaxy produced a certain amount of light and contained a certain number of stars, then the Milky Way, producing comparable light, should have a comparable population. This comparative approach was powerful because it bypassed many of the difficulties of observing from inside the galaxy. But it introduced its own uncertainties. Was the Milky Way truly typical of its class? How well did observations of external galaxies account for faint stars and dust extinction? Could differences in star formation history or chemical composition affect the comparison? As these theories developed, minds divided. Some astronomers favored the luminosity function approach, trusting the detailed studies of nearby star populations and the statistical methods used to extrapolate them. Others preferred mass-based estimates, believing that gravitational measurements provided a more reliable foundation. Still others looked to external galaxies for guidance, arguing that a broader cosmic perspective was necessary. The debates were not hostile, but they were real. Papers were published presenting different estimates. Conferences hosted discussions where proponents of different methods defended their approaches. The scientific process was working as it should, with multiple lines of evidence being pursued, compared, and reconciled. Most methods pointed toward a number in the hundreds of billions. Whether the result was closer to 100 billion or 400 billion remained uncertain, but the order of magnitude was clear. The Milky Way was not a small galaxy. It was a major spiral system containing a substantial fraction of the stars in the local universe. But even with this consensus, divisions remained. Some studies emphasized the importance of accounting for brown dwarfs, arguing that these substellar objects might add significantly to the total if they were classified as stars. Others focused on stellar remnants, suggesting that billions of white dwarfs and neutron stars should be included in any complete census. There were also theoretical divisions about the galaxy's history. Some models suggested the Milky Way had grown primarily through in situ star formation, meaning most of its stars formed within the galaxy itself. Others argued for significant contributions from mergers with smaller satellite galaxies, bringing populations of stars formed elsewhere. These different histories would produce different distributions of stellar types and different total numbers. The theories also divided over the role of dark matter. Everyone agreed that dark matter dominated the galaxy's mass, but its exact distribution and its influence on star formation remained debated. Did dark matter halos simply provide gravitational scaffolding, or did they play a more active role in shaping where and how stars formed? Different answers led to different models and different estimates of stellar populations. Through all these divisions, a pattern emerged. No single theory could answer the question definitively. Each approach had strengths and weaknesses. Each provided valuable insights but also introduced uncertainties. The true answer, if there was one, would come not from choosing between theories but from synthesizing them, from combining the insights of multiple methods into a more complete picture. And so the theories continued to evolve, refined by new data, challenged by new observations, adjusted as understanding deepened. Minds remained divided on the details, but they were united in the pursuit. Everyone wanted to know how many stars filled our galaxy. They simply disagreed on the best path to finding out. The theories represent humanity's attempt to impose order on enormity, to develop frameworks that make the uncountable countable. They are tools for approaching the impossible, methods for extracting answers from incomplete information. They are imperfect, but they are powerful, and together they have brought us closer to understanding the true scale of our galactic home, even if the exact number remains elusive. Discovery is never a single moment. It is a pursuit that unfolds across generations, built on patience, persistence, and the accumulated effort of thousands of people who dedicated their lives to a single question. For astronomers trying to count the stars of the Milky Way, that pursuit has spanned more than a century, driven by improving technology, refining methods, and an unwavering desire to understand the scale of our cosmic home. The investigation began in earnest in the early 20th century, when photography transformed astronomy from an art of visual observation to a science of recorded data. Photographic plates could capture light over long exposures, revealing stars too faint for the human eye to see. They created permanent records that could be studied, measured, and compared years or even decades later. For the first time, astronomers could build comprehensive catalogues, not just of hundreds of stars, but of thousands, then millions. One of the earliest systematic surveys was the Henry Draper Catalogue, begun in the 1880s and expanded through the early 20th century. It classified stars by their spectra, the patterns of light and dark lines that revealed their composition and temperature. By the time it was completed, it included more than 200,000 stars, each one carefully photographed and analysed. It was a monumental achievement, but it represented only a tiny fraction of the Milky Way's population, limited to the brightest and nearest stars. As the 20th century progressed, surveys grew more ambitious. The Palomar Observatory Sky Survey, conducted in the 1950s, photographed the entire northern sky visible from California, creating a comprehensive atlas that became the foundation for decades of research. Similar surveys covered the southern sky from observatories in Chile and Australia. Together, these surveys catalogued millions of stars, providing the raw material for statistical studies of the galaxy's structure and population. But photography had limitations. It was best suited for bright objects and struggled to detect the faintest stars. It required large telescopes, clear skies, and countless hours of patient observation. And it could only observe invisible light, meaning vast populations hidden by dust remained invisible. The pursuit accelerated in the late 20th century, with the development of electronic detectors called CCDs, charge-coupled devices. These silicon chips could capture light with far greater sensitivity than photographic film, recording fainter objects in shorter exposure times. They also produced digital data that could be analyzed by computers, enabling automated surveys on a scale previously unimaginable. The Sloan Digital Sky Survey, launched in the late 1990s, was one of the first major surveys to fully embrace this technology. It used a dedicated telescope in New Mexico to photograph and measure the spectra of millions of stars and galaxies. Over the course of more than a decade, it mapped about 1/3 of the sky, creating a three-dimensional atlas that revolutionized our understanding of the Milky Way structure. But even the Sloan survey could not see everywhere. The plane of the Milky Way, where most stars reside, is heavily obscured by dust in visible light. To pierce that veil, astronomers turned to infrared observations. Infrared light has longer wavelengths than visible light and can pass through dust clouds relatively unhindered. Satellites, like the Infrared Astronomical Satellite, launched in 1983, and later the Spitzer Space Telescope and the Wide Field Infrared Survey Explorer, mapped the galaxy in infrared wavelengths, revealing populations of stars that had been completely hidden before. These infrared surveys were revelations, regions that appeared as dark patches in visible light, blazed with stars in infrared. The central bulge of the galaxy, almost invisible from Earth due to dust, was revealed to be densely packed with hundreds of billions of stars. The spiral arms, traced by young bright stars in visible light, were shown to contain vast numbers of older, cooler stars as well. The total count climbed as each new population was added to the census. The pursuit also moved into space. Ground-based telescopes, no matter how powerful, are limited by Earth's atmosphere, which blurs and distorts starlight. Space telescopes, orbiting above the atmosphere, can observe with unprecedented clarity. The Hubble Space Telescope, launched in 1990, provided stunning images of distant stars and galaxies, resolving objects too faint and too crowded to separate from the ground. Later missions like the Gaia spacecraft, launched by the European Space Agency in 2013, took the pursuit to an entirely new level. Gaia's mission was to create the most precise three-dimensional map of the Milky Way ever made. It measured the positions, distances, and motions of more than 1 billion stars, about 1% of the galaxy's total population. By tracking how stars moved through space, Gaia revealed not just where they were but how they orbited, allowing astronomers to reconstruct the galaxy's structure in exquisite detail. It identified streams of stars stripped from dwarf galaxies that had merged with the Milky Way billions of years ago. It traced spiral arms and found unexpected features like ripples in the disk, evidence of ancient collisions that still echo through the galaxy's dynamics. Gaia's data transformed the investigation. With precise distances to 1 billion stars, astronomers could calibrate their methods more accurately, refining estimates of the total population. They could test theories about how stars were distributed, comparing models to reality with unprecedented precision. And they could identify rare types of stars, like white dwarfs and binary systems, that had been too difficult to study before. But even Gaia could not see all the stars. It was limited by brightness, unable to detect the faintest red dwarfs and brown dwarfs. It struggled in the crowded regions near the galactic center where stars overlapped in its field of view. And it observed primarily in visible and near-infrared wavelengths, missing populations that shone only in other parts of the spectrum. The pursuit of counting the Milky Way stars has never been the work of a single observatory or a single survey. It has required combining data from dozens of telescopes across all wavelengths, from radio to X-ray. Radio telescopes traced hydrogen gas, revealing the spiral structure and hinting at regions of ongoing star formation. X-ray observatories found compact stellar remnants like neutron stars and black holes. Ultraviolet satellites detected hot young stars and white dwarfs. Each wavelength added another layer to the picture. The investigation also required developing sophisticated computer models, simulating the galaxy's evolution from its formation to the present day allowed astronomers to predict what populations should exist and in what proportions. These simulations could then be compared to observations, refining both the models and the understanding of the real galaxy. If the simulation produced too many massive stars or too few red dwarfs, the parameters had to be adjusted. Over decades of iteration, the models converged towards something that matched reality, providing independent estimates of the total stellar population. Throughout this pursuit, astronomers faced the fundamental challenge that they could only sample, never complete. No survey could observe every star. The best they could do was measure carefully chosen regions, build statistical profiles, extrapolate to the whole. This required trusting that the samples were representative, that the unseen populations followed the same patterns as the seen ones. It was an act of scientific faith, grounded in evidence but never perfectly verifiable. The pursuit also required international collaboration. No single nation or institution could build all the telescopes, conduct all the surveys, or analyze all the data. Astronomers from around the world contributed observations, shared findings, and built upon each other's work. The question of how many stars filled the Milky Way belonged to humanity, not to any single group. The answer, when it came, would be a collective achievement. As the investigation progressed, the estimates narrowed. Early guesses of a few billion stars gave way to tens of billions, then hundreds of billions. By the turn of the 21st century, most studies converged on a range between 100 billion and 400 billion stars, depending on assumptions about faint populations and definitions of what counted as a star. That range was still wide, but it was far narrower than the range of possibility just decades earlier. The pursuit continues today. New telescopes like the James Webb Space Telescope, launched in 2021, can see even deeper into dusty regions, revealing stars that were previously invisible. Future missions will map more of the sky, detect fainter objects, and refine the measurements. The exact number may always remain uncertain, but each new observation brings us closer. And in that pursuit, in that patient accumulation of knowledge across generations, there is something profoundly human. The question of how many stars fill our galaxy is not just scientific. It is existential. It asks about our place, our context, our cosmic neighborhood. It asks whether we are rare or common, isolated or surrounded. The pursuit of an answer is a pursuit of understanding ourselves, of knowing where we stand in the vast architecture of the universe. The investigation is not finished. It may never be finished, but it has given us something precious. Not perfect knowledge, but sufficient knowledge. Not exact numbers, but meaningful estimates. Not certainty, but confidence. We know now, beyond doubt, that we live in a galaxy containing hundreds of billions of stars. The details may shift, but the scale is established. And that is the gift of the pursuit. Not just the answer, but the journey toward it. The decades of observation, the improvements in technology, the collaboration across borders and generations. The pursuit itself is a testament to human curiosity, to our refusal to accept mystery when understanding might be within reach. It is a story of looking up at the night sky and asking, how many? And then spending lifetimes trying to find out. In science, data is the foundation of everything. Theories can be elegant, methods can be clever, but without data, there is no anchor to reality. The question of how many stars fill the Milky Way has been answered not with a single observation, but with an accumulation of data points, measurements, and fragments of information gathered over decades from telescopes across the world and in space. Each piece is incomplete on its own, but together they form a picture, imperfect but revealing. The most fundamental data comes from star counts. Astronomers point telescopes at carefully chosen patches of sky and simply count the stars they see, recording their positions and brightness. This was done first by eye, then with photographic plates, and now with digital detectors. Each survey produces a catalogue, a list of stars with their coordinates and properties. The Henry Draper catalogue had hundreds of thousands of entries. Modern surveys like Gaia have over 1 billion, but star counts alone are not enough. Knowing how many stars you can see in a patch of sky does not tell you how many exist in total. You need to understand what fraction of stars you are detecting. For that, you need distance measurements. Distance is the key that transforms two-dimensional sky positions into three-dimensional maps. The most reliable method for nearby stars is parallax, the apparent shift in a star's position as Earth orbits the Sun. Nearby stars appear to shift slightly against the background of more distant ones, and by measuring that shift, astronomers can calculate distance. The smaller the shift, the farther the star. For centuries, parallax was too small to measure for all but the very nearest stars. But technology improved. The European Space Agency's Hipparcos satellite, launched in 1989, measured parallax for more than 100,000 stars. Gaia, launched in 2013, extended this to over 1 billion stars with precision 100 times better. With these distances, astronomers could place stars in three-dimensional space, mapping the structure of the Milky Way directly. Another crucial type of data comes from spectroscopy. When starlight is split into its component wavelengths, it reveals patterns of absorption and emission lines unique to each star. These lines tell us the star's temperature, composition, and motion. By studying the spectrum, astronomers can determine what type of star they are observing, whether it is a massive blue giant or a cool red dwarf, whether it is young and metal-rich or ancient and metal-poor. Spectroscopy also reveals velocity. The Doppler effect, the same phenomenon that changes the pitch of a passing siren, shifts spectral lines depending on whether a star is moving toward or away from us. By measuring these shifts, astronomers can determine how stars orbit the galaxy, tracing the rotation curve that reveals the galaxy's mass distribution. Infrared data has been transformative. Stars emit radiation across the spectrum, but cool objects shine brightest in infrared. Red dwarfs, which dominate the galaxy by number, are faint in visible light but more prominent in infrared. Brown dwarfs, too cool to shine brightly at any wavelength, glow faintly in infrared. Dust, which blocks visible light, is transparent to longer infrared wavelengths. Surveys like the 2-micron all-sky survey, completed in 2001, mapped the entire sky in near-infrared light, revealing millions of stars hidden by dust. The Spitzer Space Telescope, and later the Wide-Field Infrared Survey Explorer, extended these observations, cataloguing populations that had been completely invisible before. Each new survey added clues, filling in gaps in the census. Radio data contributes differently. Radio telescopes do not detect stars directly, but they map hydrogen gas, the raw material from which stars form. By tracing the distribution of gas, astronomers can infer where star formation is occurring and estimate how many stars should exist in those regions. Radio observations also revealed the spiral structure of the Milky Way, showing how gas concentrates along the arms where stars are born. X-ray observations provide yet another layer. X-rays come from extremely hot or energetic sources like neutron stars, black holes, and the hot gas surrounding massive stars. X-ray surveys have catalogued tens of thousands of compact objects, stellar remnants that no longer shine in visible light but remain part of the galaxy's population. These objects are difficult to detect, but they contribute to the total count if you define stars broadly enough to include their remnants. Each type of data has its own biases and limitations. Visible light surveys miss dust-obscured regions. Infrared surveys struggle with crowded fields where stars overlap. Parallax measurements lose accuracy at large distances. Spectroscopy requires collecting enough light to analyze, limiting it to brighter objects. Radio and X-ray observations capture specialized populations but miss the majority of ordinary stars. To build a complete picture, astronomers combine data from many sources. They use statistical techniques to account for what each survey can and cannot see. They build models that predict what the unseen populations should look like based on the visible ones. They cross-reference catalogues, matching stars observed in different wavelengths to build comprehensive profiles. One powerful clue comes from the luminosity function, the distribution of stars by brightness. By carefully studying nearby regions where even faint stars can be detected, astronomers determine how many stars exist at each luminosity level. This distribution follows predictable patterns. For every bright star, there are many more dim ones. By measuring this ratio in well-studied regions, it can be applied to the galaxy as a whole, estimating the total population, including the stars too faint to detect directly. Another clue comes from the galaxy's total light output. By measuring how much light the Milky Way emits and comparing it to the light per star for different stellar types, astronomers can estimate the stellar population. This requires assumptions about the mix of stellar types, but it provides an independent check on other methods. Mass measurements offer yet another clue. By studying how stars and gas orbit the galaxy, astronomers can determine the total gravitational mass. Subtracting the mass of gas and dark matter leaves the mass in stars. Dividing by the average stellar mass gives an estimate of the number of stars. This method is indirect, depending heavily on understanding dark matter and the mass distribution, but it consistently points toward hundreds of billions of stars. Comparisons with external galaxies provide additional data. Astronomers observe spiral galaxies similar to the Milky Way and measure their properties. How much light do they emit? What is their rotation curve? How many stars do detailed studies reveal? By finding galaxies that resemble our own, the observations can be used as analogies, inferring what the Milky Way's population should be based on these external templates. All of these data sources, these clues and fragments, must be synthesized. No single measurement tells the whole story, but when combined, weighted, and analyzed, they converge on a range. Most estimates fall between 100 billion and 400 billion stars. The spread reflects uncertainty in the faint end of the luminosity function, in the amount of dust obscuration, in the definition of what counts as a star. The data also reveals structure. The Milky Way is not a uniform distribution of stars. The central bulge is densely packed, containing perhaps a quarter of the galaxy's stars in a relatively small volume. The disk is structured into spiral arms where young stars concentrate. The halo is sparse, containing ancient globular clusters and scattered field stars. Each region has its own stellar population, its own characteristics, its own contribution to the total. The fragments of data show variations in age, composition, and distribution. Stars in the bulge are mostly old, formed early in the galaxy's history. Stars in the disk span a range of ages, from ancient to newborn. The spiral arms are rich in young, massive stars, while the spaces between contain older populations. This diversity must be accounted for in any complete census. The data is incomplete. It will always be incomplete. We can observe only a fraction of the Milky Way's stars directly, but the fraction we do observe is carefully chosen, statistically representative, and supplemented by indirect evidence. The clues and fragments, when assembled with care, produce a coherent picture. That picture shows a galaxy of hundreds of billions of stars, most of them small and dim, invisible without powerful telescopes, but nonetheless real and countable through statistical methods. The data does not give us an exact number, but it gives us confidence in the scale. The Milky Way is not a small collection. It is a major galaxy, rich, with stars comparable to other large spirals in the universe. The pursuit of data continues. Every new survey adds more stars to catalogues. Every new wavelength reveals previously hidden populations. Every improvement in instrumentation allows detection of fainter, more distant objects. The fragments accumulate, the picture sharpens, and the estimates narrow. But the data will never be complete. That is the nature of observing from inside a vast system, of trying to count something too large to see all at once. We work with what we can observe, infer what we cannot, and build models to bridge the gap. The data is fragmentary, but it is sufficient to answer the question not with perfect precision, but with meaningful certainty. Hundreds of billions of stars. That is what the data tells us. Not a guess, not a hope, but an estimate grounded in measurements, observations, and careful analysis. The clues and fragments, assembled with patience and skill, reveal the scale of our galactic home. The more astronomers learned about the Milky Way, the more they realized how much was hidden from view. Not hidden in the sense of being unknowable, but hidden by the simple physical realities of distance, faintness, and obstruction. The deeper mystery was not just how many stars filled the galaxy, but how many types of stars existed, how they were distributed, and what the vast invisible majority looked like. The visible stars, the ones that dominate our night sky and fill star catalogues, represent only a small fraction of the total population. They are the bright outliers, the rare giants and supergiants that shine powerfully enough to be seen across thousands of light years. But they are not typical. The typical star in the Milky Way is something we rarely see, a red dwarf. Red dwarfs are small stars, with masses ranging from about 8% to 50% that of the Sun. They burn their hydrogen fuel slowly, glowing with a dim red light that makes them almost invisible at any significant distance. None of the stars visible to the naked eye are red dwarfs, because even the nearest ones are too faint for human eyes to detect. Yet they may constitute 70 or even 80% of all stars in the galaxy. This was the hidden truth. The galaxy was not dominated by bright, sun-like stars. It was dominated by an invisible majority of small, cool, faint stars that could only be detected with telescopes, and then only if they were relatively nearby. If you could somehow make your eyes sensitive enough to see red dwarfs, the night sky would not contain a few thousand visible stars. It would contain millions, perhaps billions if you could see far enough, all glowing with faint red light. The implications were profound. If most stars were red dwarfs, and if red dwarfs were so difficult to detect, then any census of the galaxy that relied on visible light was dramatically incomplete. Early estimates that counted primarily bright stars were missing, the majority of the population. The true number could be several times higher than what simple star counts suggested. As infrared surveys began revealing these hidden populations, the estimates climbed. Surveys that could detect faint red dwarfs found them everywhere, outnumbering brighter stars by wide margins. Statistical analyses of stellar populations confirmed that the luminosity function dropped steeply toward the faint end, meaning there were far more dim stars than bright ones. But red dwarfs were not the only hidden population. Brown dwarfs, objects too small to sustain full hydrogen fusion, occupied a grey area between stars and planets. They formed like stars, collapsing from clouds of gas, but lacked the mass to ignite lasting fusion in their cores. Instead, they glowed faintly from the heat of their formation and from brief periods of deuterium fusion in their youth, then cooled slowly over billions of years. Brown dwarfs were almost impossible to detect. They shone primarily in infrared wavelengths, and even then they were faint. The first brown dwarf was not definitively identified until 1995, and for years they remained rare curiosities. But as surveys improved, particularly in infrared, astronomers began finding more. It became clear that brown dwarfs were not rare at all. They might number in the billions, scattered throughout the galaxy, invisible to most surveys but nonetheless real. The question of whether to count brown dwarfs as stars was contentious. They formed like stars, they had similar compositions, but they did not fuse hydrogen. Some astronomers argued they should be included in any complete census. Others insisted they were a separate category, neither star nor planet, but something in between. The definition mattered because it could change the total by tens of billions. Another hidden population consisted of stellar remnants. When stars die, they leave behind white dwarfs, neutron stars, or black holes, depending on their initial mass. These objects are the corpses of former stars, no longer shining through fusion but still contributing to the galaxy's mass and structure. White dwarfs are the most common remnants, the final state of stars like the Sun. They are incredibly dense, packing about the mass of the Sun into an object the size of Earth. They glow faintly from residual heat, slowly cooling over billions of years. Because they are so small and dim, they are difficult to detect unless they are very nearby, or happen to be part of a binary system where they interact with a companion. Neutron stars are even more extreme. The collapsed cores of massive stars left behind after supernova explosions. They pack more than the Sun's mass into a sphere just 20 kilometers across, creating densities so extreme that atoms collapse, leaving only neutrons. Most neutron stars are invisible, detectable only if they happen to be pulsars, spinning rapidly and beaming radiation like cosmic lighthouses. Otherwise, they are dark points of mass drifting through the galaxy. Black holes are the ultimate hidden population. They emit no light, absorb everything, and can only be detected indirectly through their gravitational effects on nearby matter. Stellar mass black holes, formed from the collapse of massive stars, may number in the hundreds of millions throughout the galaxy, but only a tiny fraction have been identified. Should these remnants be counted among the stars? They were stars once. They formed from star-forming clouds, lived stellar lives, and left behind compact objects that still mark their presence. If the question is, how many stars the galaxy ever formed, the answer includes remnants. If the question is how many currently fusing stars exist, it does not. The hidden truth was that definition mattered as much as observation. Dust itself was part of the hidden truth, not just because it obscured stars, but because it shaped where and how stars formed. Interstellar dust was not inert. It was part of the galaxy's ecosystem, cycling through star formation, stellar winds, and supernova explosions. Stars formed in dust clouds, enriched the clouds with heavy elements when they died, and the enriched clouds formed new generations of stars. The hidden truth extended to structure. The Milky Way's spiral arms, so prominent in images, were regions of enhanced star formation. But they were not permanent features. They were density waves, patterns that rotated through the galaxy more slowly than the stars themselves. Stars entered spiral arms, experienced compression that triggered star formation, then exited into the quieter regions between arms. The spiral structure was real, but it was a pattern imposed on a more evenly distributed population. The central bulge hid its own truths. It was densely packed with stars, but it was also heavily obscured by dust. Infrared surveys revealed that the bulge contained not just old stars, but a bar-shaped structure extending thousands of light years, influencing the orbits of stars and the flow of gas throughout the inner galaxy. This bar had been debated for decades before observations confirmed it, and its presence changed understanding of the galaxy's dynamics and history. The halo held hidden populations as well. Streams of stars, remnants of dwarf galaxies torn apart by the Milky Way's gravity, traced paths through the outer regions. These streams were subtle, requiring careful analysis to detect, but they revealed the violent history of galactic growth. The Milky Way had not formed in isolation. It had grown by consuming smaller neighbours, and their stars now mixed with the original population, hidden in plain sight unless you knew how to look. The deeper mystery was that every method of observation revealed a different aspect of the truth. Visible light showed the bright stars. Infrared revealed the faint red dwarfs and brown dwarfs. Radio traced the gas. X-rays found compact remnants. Each wavelength exposed a hidden population, and only by combining them all could the full picture emerge. And even then, the picture remained incomplete. There were stars too faint to detect, regions too obscured to see, objects too dark to observe. The hidden truth was that we would never have a perfect census. There would always be populations we could only infer, never directly observe. The galaxy's true number of stars was hidden not by conspiracy or impossibility, but by the limitations of observation and the vastness of what we were trying to count. Yet the hidden truth did not make the question unanswerable. It made it richer, more nuanced, more dependent on careful definition and statistical inference. The answer was not a single number, but a range, an estimate that accounted for the visible and invisible, the detected and inferred. The deeper mystery revealed that hundreds of billions was not just a count of bright stars, but a census that included the invisible, majority. The hidden populations that truly defined the galaxy's scale. The Milky Way was full of light, but it was even more full of stars that barely shone at all. And in that hidden truth lay both the challenge and the wonder of trying to count them. There comes a moment in every scientific pursuit when the approach itself must change, when the methods that served for decades prove inadequate, when the very framework of thinking shifts to accommodate new understanding. For the question of how many stars fill the Milky Way, that turning point came when astronomers realized they could not simply count stars and extrapolate. They needed to understand populations, distributions, and the physical processes that shaped the galaxy's structure. The old paradigm was straightforward. Count stars in a region, measure their density, multiply by the galaxy's volume, and arrive at a total. This worked reasonably well for rough estimates, but as observations improved and the complexity of the galaxy became clear, it was obvious that this approach was insufficient. The galaxy was not uniform. Different regions had vastly different star densities. Different types of stars dominated in different locations, and most stars were too faint or too obscured to count directly. The paradigm shift was to stop trying to count everything and start modeling populations. Instead of asking how many stars we see and extrapolating, astronomers began asking what kinds of stars should exist based on the physics of star formation, how those different types should be distributed, and how their properties would affect what we observe. This shift was enabled by advances in computer modeling. Simulations could recreate the entire life cycle of star formation, from the collapse of gas clouds to the ignition of fusion to the evolution and death of stars over billions of years. By running these simulations and comparing the results to observations, astronomers could refine their understanding of what the galaxy's true population should look like. The key insight was the initial mass function, a mathematical description of how many stars form at different masses. Observations of nearby star-forming regions showed a clear pattern. For every massive star that formed, dozens of medium-mass stars formed, and hundreds or thousands of low-mass stars formed. This distribution was not random. It reflected the physics of fragmentation in collapsing gas clouds, where gravitational instabilities naturally favored the formation of small objects over large ones. By applying the initial mass function to the entire galaxy, astronomers could estimate how many stars of each type should exist, even if they could not observe them all directly. If nearby regions showed that red dwarfs outnumbered sun-like stars by 10 to 1, then that ratio could be applied galaxy-wide. If brown dwarfs formed at a certain rate relative to true stars, that rate could be incorporated into the models. This statistical approach transformed the question. It was no longer necessary to count every star individually. It was sufficient to understand the population distribution and apply it to the regions that could not be observed directly. The paradigm shifted from direct observation to informed inference. Another aspect of the shift involved recognizing that the galaxy had a history. It was not a static collection of stars frozen in time. It had formed 13 billion years ago and had been evolving ever since. Stars formed, lived, and died. The galaxy merged with smaller neighbors, cannibalizing their stars. Gas flowed inward along spiral arms, triggering bursts of star formation. The stellar population at any given moment was shaped by this long history. Computer simulations of galactic evolution allowed astronomers to model this history, starting from initial conditions shortly after the Big Bang and evolving forward through billions of years. These simulations predicted what the present-day population should look like, how many stars of different ages and compositions should exist, and where they should be located. Comparing simulations to observations provided a reality check, confirming or challenging the models and leading to refinements. The paradigm shift also involved embracing uncertainty as part of the answer. The old approach aimed for a single number, a definitive count. The new approach accepted that the best answer was a range, a distribution of possible values based on different assumptions about unseen populations and definitions of what counted as a star. This was not a failure of precision but an acknowledgement of reality. The question was too complex for a single number, but it was not too complex for a well-constrained estimate. As this shift took hold, the estimates converged. Different methods, different surveys, different models, all pointed toward the same order of magnitude. Whether the final number was 100 billion or 400 billion depended on details, but all serious estimates fell within that range. The paradigm shift brought consensus, not through agreement on exact figures, but through agreement on the framework for arriving at those figures. The turning point also changed how astronomers communicated the answer. Instead of proclaiming a specific number, they presented ranges with caveats. They explained that the answer depended on whether you counted brown dwarfs, whether you included stellar remnants, whether you accounted for the faintest red dwarfs. They acknowledged the uncertainties while still conveying the fundamental truth. The galaxy contained hundreds of billions of stars, and that scale was robust, regardless of the exact definition. This shift in communication reflected a maturation of the field. Early estimates were often presented with more confidence than the data warranted, partly because the complexity of the problem was not fully appreciated. As understanding deepened, so did humility. The new paradigm accepted that some questions do not have perfect answers, but that imperfect answers could still be meaningful and useful. The paradigm shift also had practical implications. Space agencies planning missions to map the galaxy could use population models to predict what their instruments should see, guiding the design of surveys and the interpretation of data. Researchers studying exoplanets could estimate how many planetary systems might exist based on the stellar population, informing searches for life elsewhere. Theoretical work on galaxy formation and evolution could be tested against the Milky Way's observed properties, using our galaxy as a laboratory for understanding galaxies across the universe. Looking back, the turning point was less a single moment than a gradual transformation spread across decades. But key developments marked the shift: the recognition that red dwarfs dominated by number, the development of the initial mass function, the rise of computer simulations capable of modeling entire galaxies, the launch of infrared surveys that revealed hidden populations. Each of these milestones pushed the field toward the new paradigm. Today, the question of how many stars fill the Milky Way is approached not as a counting problem but as a population modeling problem. The answer emerges from a synthesis of observations, simulations, statistical methods, and physical understanding. It is more sophisticated, more nuanced, and more robust than the simple extrapolations of earlier generations. The paradigm shift did not make the question easier to answer, but it made the answer more reliable. It transformed uncertainty from a weakness into a feature, acknowledging what we do not know while clearly stating what we do. It brought the question into the modern era of astronomy, where big data, powerful computers, and deep physical insight combined to tackle problems that once seemed intractable. The turning point was the realization that we do not need to see every star to count them. We need to understand the principles that govern their formation, distribution, and evolution. With that understanding, inference becomes as powerful as observation, and the answer, though still uncertain in its details, becomes clear in its essence. Hundreds of billions of stars. That is the paradigm. That is the turning point from which all modern estimates proceed, and it is a testament to the power of science to transform impossible questions into answerable ones, not by simplifying them, but by developing the tools to embrace their full complexity. Every major shift in understanding sends ripples through a field of study, changing not just the answer to one question, but reshaping how related questions are approached. When astronomers settled on the understanding that the Milky Way contained hundreds of billions of stars, the immediate consequences rippled outward, touching everything from the search for planets to the possibility of life. From our understanding of galactic structure to our place in the cosmic hierarchy. The first and most direct consequence was a re-evaluation of planetary systems. If the galaxy contained hundreds of billions of stars, and if even a modest fraction of them hosted planets, then the number of worlds in the Milky Way could be staggering. Early in the history of astronomy, planets were known only in our solar system. The idea that other stars might have their own retinue of worlds was speculation, occasionally discussed but never proven. That changed in the 1990s with the discovery of the first exoplanets. As detection methods improved, astronomers found planets around more and more stars. It became clear that planets were not rare. They were common, perhaps even the norm. Surveys suggested that most stars had at least one planet, and many had multiple worlds in complex systems. The consequence was immediate. If hundreds of billions of stars meant hundreds of billions of potential planetary systems, then the galaxy might contain not just billions but trillions of planets. Among those trillions, a substantial fraction would lie in habitable zones, regions where temperatures allowed liquid water to exist. The possibility of life elsewhere, once a philosophical question with no data, became a statistical one with increasingly favorable odds. This realization transformed the search for extraterrestrial life. If habitable worlds were common, then life might be as well. The question shifted from whether life existed elsewhere to how common it might be and where we should look for it. Missions like Kepler, which surveyed thousands of stars for transiting planets, were designed with the understanding that the galaxy's stellar abundance meant abundant opportunities for worlds. The discovery that planets were ubiquitous was a direct consequence of knowing the scale of the stellar population. Another consequence touched the structure of the Milky Way itself. Understanding that the galaxy contained hundreds of billions of stars, most of them faint and many hidden, forced astronomers to revisit their models of galactic dynamics. The distribution of stars, the density of different regions, the thickness of the disk, all had to account for populations that previous generations had missed. The central bulge, once thought to contain perhaps 10 or 20 billion stars, was revealed to hold far more, perhaps a quarter of the galaxy's total population, packed into a relatively small volume. This changed understanding of the bulge's formation. If it was so massive and so densely populated, it must have formed early in the galaxy's history through rapid gas infall and star formation. It could not have grown gradually over time, or its stars would be more spread out. The spiral arms, too, were reinterpreted. If most stars were faint red dwarfs, then the bright young stars that traced the spiral structure were only markers, highlighting regions of recent star formation, but not representing the bulk of the stellar mass. The arms were features of the young population, but the overall mass distribution was smoother, dominated by older, fainter stars distributed throughout the disk. The halo gained attention as well. If the galaxy contained hundreds of billions of stars, where were the oldest ones? Many resided in globular clusters, but many more drifted as field stars in the halo, difficult to detect individually but collectively significant. Understanding the halo population helped reconstruct the galaxy's early history, showing how it grew from smaller fragments that merged and accreted. The consequence for dark matter was subtle but important. Knowing the stellar population allowed better estimates of the galaxy's total visible mass. By comparing this to the mass inferred from rotation curves, astronomers could determine how much dark matter surrounded the galaxy. The ratio of dark matter to stellar matter became a key observational constraint for theories of galaxy formation, showing that dark matter dominated not by a small margin but by a factor of 5 or more. Another ripple affected the study of stellar populations in other galaxies. If the Milky Way contained hundreds of billions of stars with a certain distribution of types and ages, then galaxies of similar brightness should have similar populations. This allowed astronomers to estimate stellar numbers in galaxies too distant for individual stars to be resolved, extending the census beyond our own to the broader universe. The Milky Way became a template, a calibration point for understanding galaxies across cosmic history. The immediate consequence for science communication was equally significant. Hundreds of billions of stars was a number that captured imagination in ways that millions or even tens of billions did not. It conveyed scale in a way that felt vast but not incomprehensible. It provided a talking point, a way to explain the galaxy to the public in terms that emphasized its richness and abundance. Every planetarium show, every documentary, every educational program about the Milky Way now included that figure, hundreds of billions of stars, as a central fact. For younger generations of astronomers, the consequence was a shift in focus. Counting stars was no longer the cutting edge. The number was known well enough. Instead, attention turned to understanding the diversity of those stars, to mapping their distributions, to studying rare types and exceptional objects. The question evolved from how many to what kinds and where. The immediate ripple also affected how we thought about ourselves. Knowing that the galaxy contained hundreds of billions of stars forced a reckoning with scale. Earth orbited one ordinary star among hundreds of billions. The Sun was not special in any meaningful sense. Our entire solar system, everything humans had ever known or explored, was a single point in a sea of incomprehensible abundance. This could feel diminishing, reducing humanity to insignificance, but it could also feel liberating, opening vast possibilities. If the galaxy was so large, if it contained so many stars and so many potential worlds, then the universe was richer than we had imagined. We were part of something immense, and our questions about life, intelligence, and meaning extended across a stage far grander than any previous generation had contemplated. The consequence was also practical for space agencies and research priorities. Missions to study the Milky Way's structure, to map its stars, to search for exoplanets and signs of life, all gained justification from the knowledge that the targets were abundant. Funding agencies could see that the potential return on investment was enormous. With hundreds of billions of stars, there were hundreds of billions of opportunities for discovery. The ripples reached into philosophy and culture as well. Writers, filmmakers, and artists drew on the scale of the galaxy to craft stories of exploration, contact, and wonder. The phrase, hundreds of billions of stars, became shorthand for the vastness of the cosmos. A reminder that we were only beginning to explore our own neighborhood. The immediate consequence of settling on hundreds of billions was not a single event, but a wave of changes that touched every aspect of galactic astronomy and beyond. It reshaped priorities, opened new questions, and provided a framework for understanding our place in the universe. The number itself was just a starting point, but it set in motion decades of research and discovery that continues today. The ripple effects will continue for generations. Every new mission, every new survey, every new discovery about the Milky Way builds on the foundation of knowing its scale. The consequence of answering one question, how many stars, was the opening of countless others. And in those new questions lies the future of our exploration, our understanding, and our wonder at the galaxy we call home. Some scientific discoveries fade into history, remembered as milestones but not as living truths that shape ongoing research. Others continue to resonate, their implications unfolding across decades, touching fields and questions far beyond their original scope. The understanding that the Milky Way contains hundreds of billions of stars is one of those enduring discoveries. Its impact echoes through time, shaping how we study the universe, how we search for life, and how we understand our own existence. The most profound long-term impact has been on the search for extraterrestrial intelligence. When Frank Drake formulated his famous equation in 1960, estimating the number of communicating civilizations in the galaxy, the first term was the rate of star formation. But beneath that term lay an assumption about the total number of stars. If the galaxy contained only a few billion stars, the odds of finding another civilization were slim. With hundreds of billions, the odds improved dramatically. Every term in the Drake equation multiplied uncertainties, but the foundational scale mattered. A galaxy of hundreds of billions of stars meant hundreds of billions of opportunities for planetary systems, for habitable worlds, for the emergence of life, for the evolution of intelligence. Even if only a tiny fraction led to communicating civilizations, the absolute numbers could still be significant. The impact of knowing the stellar population was to make SETI, the search for extraterrestrial intelligence, seem not just hopeful, but statistically plausible. Decades of radio searches have not yet found a signal, but the search continues, driven partly by the knowledge that the targets are abundant. With hundreds of billions of stars, many with planets, many with potentially habitable worlds, the silence we observe is not evidence of absence, but a reminder of scale. The galaxy is so large that even if civilizations exist, finding them requires patience, better technology, and luck. The impact of knowing the stellar count is to sustain hope across long timescales, to justify continued searching despite decades of null results. The impact extends to astrobiology, the study of life's potential throughout the universe. Knowing that red dwarfs, the most common stars, dominate the galaxy changed where astrobiologists focus attention. Red dwarfs live for trillions of years, far longer than sun-like stars. If they host habitable planets, those worlds have immense timescales for life to emerge and evolve. The abundance of red dwarfs means the abundance of these long-lived habitable zones. The impact has been a shift in research priorities, with missions now specifically targeting red dwarf systems in the search for life. The understanding of stellar abundance also shaped cosmology, the study of the universe as a whole. Galaxies are the fundamental building blocks of cosmic structure, and understanding one galaxy in detail provides a template for understanding billions of others. The Milky Way's stellar population helped calibrate models of galaxy formation and evolution, simulations that reproduced the Milky Way's properties, including its stellar mass and distribution, could be trusted to model other galaxies and earlier epochs of cosmic history. The impact reached backward in time as well. By understanding the current stellar population and its distribution of ages and compositions, astronomers reconstructed the Milky Way's history. The galaxy formed from smaller pieces that merged over billions of years. Each merger brought new populations of stars, mixing and evolving. The oldest stars, metal-poor and found primarily in the halo, revealed conditions in the early universe. Younger stars, enriched with heavy elements from generations of supernovae, traced more recent history. This historical reconstruction had implications for understanding the formation of the first galaxies after the Big Bang. If the Milky Way grew through mergers, then so did other galaxies. The process was not smooth but violent, with collisions and accretion shaping structure. Knowing the Milky Way's stellar population provided a reference point for theories of hierarchical galaxy formation, confirming that galaxies built themselves up from smaller pieces over cosmic time. The impact on stellar astrophysics was equally significant. Understanding that red dwarfs dominated by number-focused attention on their properties. For decades, they were underappreciated because they were so faint. But if they made up the majority, research into red dwarf atmospheres, magnetic activity, flare events, and habitability of their planets all accelerated because of the recognition that these stars defined the galaxy's population. Similarly, the study of brown dwarfs grew from a curiosity to a field in its own right. If brown dwarfs were abundant, they represented a significant population that occupied the boundary between stars and planets. Understanding their formation, evolution, and properties became essential for a complete picture of the galaxy. The impact of recognizing their potential numbers drove surveys to find them, missions to characterize them, and theories to explain them. The long-term impact also shaped human culture. The phrase hundreds of billions of stars entered common language as a way to express vastness. It appeared in literature, film, music, and art as a metaphor for abundance, possibility, and the incomprehensibility of the cosmos. The number became more than a scientific fact. It became a symbol of the universe's richness and our small but meaningful place within it. Philosophically, the impact was profound. If the galaxy contained hundreds of billions of stars, and if the universe contained hundreds of billions of galaxies, then the total number of stars in the observable universe reached into the hundreds of sextillions. The scale was so vast that it challenged fundamental assumptions about uniqueness and significance. Were we rare? Common? Somewhere in between? The impact was not to answer these questions, but to frame them in a way that felt both humbling and inspiring. Humbling because our sun was one among hundreds of billions. Inspiring because the galaxy's abundance suggested possibilities beyond imagination. Perhaps we were not alone. Perhaps intelligence was common. Perhaps the universe was teeming with life, waiting to be discovered. The echoes through time continue. Each new survey refines the estimate of the Milky Way's stellar population. Each new exoplanet discovery adds to the tally of known worlds. Each new model of galaxy formation incorporates the lessons learned from our own galaxy's structure. The impact of understanding the stellar count is not a single effect, but a cascade of insights that build on each other, generation after generation. Future discoveries will continue to be shaped by this knowledge. Missions to map the galaxy in even greater detail, to characterize stellar populations in distant regions, to search for life on planets around the most common stars, all build on the foundation of knowing the scale. The impact is not historical. It is ongoing, shaping research priorities and philosophical perspectives for decades to come. In a sense, the impact of knowing that the Milky Way contains hundreds of billions of stars is the impact of grasping our context. We are not at the center. We are not alone in our region. We are part of an immense system containing more stars than we can easily comprehend. That context changes everything, from the questions we ask, to the way we search for answers, to the meaning we find in our existence. The echoes through time remind us that some discoveries are not endpoints, but beginnings. Knowing how many stars fill our galaxy did not close a chapter. It opened countless new ones, each exploring a different aspect of what that abundance means. And as those echoes continue to reverberate, we are carried forward, always learning, always discovering, always gazing upward in wonder at the hundreds of billions of companions that share this galaxy with us. Behind every estimate, behind every survey, behind every incremental refinement of our understanding of the Milky Way's stellar population, astronomers who dedicated years, sometimes entire careers, to the pursuit of this single question. They were not just scientists, they were dreamers, driven by curiosity about scales that exceeded comprehension, motivated by the desire to know something fundamental about our place in the cosmos. Harlow Shapley was one such dreamer. In the early 20th century, he devoted himself to understanding the structure of the Milky Way, using globular clusters as probes of the galaxy's extent. His work required painstaking observations night after night, measuring the brightness of variable stars in distant clusters, calculating distances that pushed the boundaries of what was knowable at the time. He made mistakes, his early estimates placing the galaxy larger than it truly was, but his fundamental insight was correct. We were not at the center. The sun orbited a distant core, and the galaxy was far more vast than anyone had realized. Shapley's work was transformative, but it came at personal cost. Long hours at the telescope, the pressure to publish, the debates with colleagues who challenged his conclusions. He persisted because the question mattered to him, because understanding the galaxy's scale felt like understanding something essential about existence itself. In his later writings, he reflected on the loneliness of looking up at the night sky and realizing how small we were, how peripheral our position, how vast the system we inhabited. Another dreamer was Henrietta Swan Leavitt, whose discovery of the period luminosity relationship in Cepheid variables became the foundation for measuring cosmic distances. She worked not at a major observatory with powerful telescopes, but at the Harvard College Observatory, analyzing photographic plates taken by others. In the early 1900s, women were not allowed to operate telescopes at most institutions. They were relegated to computational work, cataloguing and measuring, considered assistants rather than scientists. Leavitt accepted these limitations and worked within them, finding patterns in data that others had overlooked. Her discovery was elegant and profound. By showing that Cepheids with longer pulsation periods were intrinsically brighter, she provided the key to measuring the galaxy's size and, eventually, estimating its stellar population. She never received the recognition she deserved during her lifetime. She died in 1921 at age 53, largely unaware of how foundational her work would become. But her contribution echoes through every distance measurement, every estimate of the Milky Way's scale. Edwin Hubble, who used Leavitt's discovery to prove that spiral nebulae were distant galaxies, became famous in ways that Shapley and Leavitt never did. His name is on one of humanity's greatest telescopes, the Hubble Space Telescope, which has revolutionized astronomy since its launch in 1990. But Hubble himself was a complex figure, ambitious and competitive, sometimes taking credit for insights that others had contributed to. He was a dreamer who wanted to be the first, the one remembered, and history granted him that wish. The dreamers of the mid-20th century faced different challenges. Jan Oort, a Dutch astronomer, worked to map the Milky Way's structure using radio observations of hydrogen gas. His work revealed the spiral arms and helped establish the Sun's distance from the galactic center. He worked through World War II, when the Netherlands was occupied and resources were scarce. Astronomy seemed like a luxury when survival was uncertain. But Oort continued, believing that understanding the universe was part of what made humanity worth preserving. Vera Rubin, studying galactic rotation curves in the latter half of the 20th century, found evidence for dark matter that would reshape understanding of galaxies, including our own. She faced discrimination throughout her career. Initially denied admission to Princeton's graduate program because they did not accept women, she persisted, conducting groundbreaking research at other institutions, and eventually received recognition late in life. Her work showed that galaxies contained far more mass than their visible stars accounted for, forcing a recalculation of everything, including the Milky Way's total mass and, indirectly, its stellar population. Rubin was a dreamer who refused to be stopped by barriers, who found ways around obstacles, who proved through persistence and brilliance that the questions she asked mattered. In interviews late in her life, she spoke about the joy of discovery, the thrill of seeing something no one had seen before, of realizing the universe was stranger and richer than anyone had imagined. The dreamers of the late 20th and early 21st centuries benefited from technology their predecessors could only imagine. Catherine Cesarski, who led the European Southern Observatory and championed infrared astronomy, helped develop instruments that could see through the dust obscuring much of the galaxy. Her work enabled surveys that revealed hidden populations of stars, dramatically increasing estimates of the Milky Way's total count. She spoke often about the importance of building tools that would outlast any individual career, instruments that future generations would use to answer questions not yet asked. The scientists behind the Gaia mission represent a newer generation of dreamers. Gaia was not the vision of a single person, but of hundreds of astronomers, engineers, and programmers who worked together over decades to build a spacecraft capable of measuring the positions and motions of 1 billion stars with unprecedented precision. The mission required international collaboration, pooling resources and expertise across borders. It was a testament to what could be achieved when dreamers worked together toward a common goal. The human element in this story is not just about famous names. It includes thousands of graduate students who spent years analyzing data, technicians who maintained telescopes and instruments, programmers who wrote software to process observations, teachers who inspired the next generation. Each person played a role, however small, in advancing our understanding of how many stars fill the galaxy. There is something deeply human about this pursuit. The question is not practical. Knowing whether the Milky Way contains 100 billion or 400 billion stars does not change daily life, does not solve hunger or disease, does not directly improve anyone's circumstances. Yet people devoted their lives to it because it mattered in a different way. It mattered because understanding where we are, what surrounds us, how many companions we have in the darkness, speaks to something fundamental about human curiosity and wonder. The dreamers were driven by different motivations. Some sought fame and recognition. Others worked quietly, content to contribute to a collective endeavor. Some were motivated by aesthetics, by the beauty of the question and the elegance of the methods developed to answer it. Others were driven by philosophy, by the desire to understand humanity's context in the universe. But they all shared one quality. They looked up at the night sky and refused to accept mystery when knowledge might be within reach. They believed that the question of how many stars filled the galaxy was answerable, even if the answer would always remain somewhat uncertain. They believed that the pursuit itself was worthwhile, that each incremental improvement in understanding was a victory, that passing the work to the next generation was a contribution to something larger than any individual life. The human element is what transforms the question from an abstract exercise into a story. It reminds us that science is not done by machines or institutions, but by people with dreams, ambitions, flaws, and persistence. Every estimate of the Milky Way's stellar population carries within it the fingerprints of those who worked to produce it. The long nights at telescopes, the years analyzing data, the frustrations of failed observations, and the joys of successful ones. In the end, the dreamers leave behind more than numbers and papers. They leave behind a legacy of curiosity, a tradition of asking questions about the universe and refusing to settle for ignorance. They inspire those who come after, showing that it is possible to dedicate your life to understanding something so vast it defies comprehension, and that the pursuit is meaningful even when the answer remains incomplete. When we say the Milky Way contains hundreds of billions of stars, we are not just stating a fact. We are honoring the dreamers who made that knowledge possible, who looked up at the darkness and asked how many companions were hiding there, who devoted their finite lives to measuring the infinite, who left the universe a little less mysterious for those of us who follow. Science thrives on disagreement, not the hostile, unproductive kind, but the constructive clash of ideas where different interpretations of evidence lead to debates that ultimately sharpen understanding. The question of how many stars fill the Milky Way has been no exception. Throughout its history, this question has sparked debates, controversies, and challenges that forced astronomers to defend their methods, refine their estimates, and confront the limitations of their observations. The first major opposition came in the early 20th century, when Harlow Shapley's estimates of the Milky Way's size challenged prevailing wisdom. Before Shapley, most astronomers believed the Sun was near the center of the galaxy and that the entire starry system was relatively modest in size, perhaps a few thousand light-years across. Shapley's work with globular clusters suggested something radically different, a galaxy 100,000 light-years or more in diameter, with the Sun relegated to the outskirts. His conclusions were met with skepticism, even hostility. Other prominent astronomers challenged his distance measurements, his assumptions about the properties of Cepheid variables, and his interpretation of the globular cluster distribution. They argued he was overestimating distances, that his methods contained systematic errors, that the galaxy could not possibly be as large as he claimed. The opposition was not without merit. Shapley's initial estimates were too large, later revised downward as techniques improved. But the fundamental insight that we were not central and that the galaxy was far more vast than previously thought survived scrutiny. The battle for truth was resolved through better observations, independent verification, and the gradual accumulation of evidence that supported Shapley's core claims, even as it corrected his errors. A related controversy erupted over the nature of spiral nebulae. Were they nearby gas clouds within the Milky Way, or were they distant galaxies in their own right? Shapley believed they were local. Heber Curtis argued they were external. The debate reached a climax in the famous 1920 Great Debate, a formal discussion between the two astronomers that laid out the evidence on both sides. Neither side convinced the other at the time, but the controversy drove observers to seek better data. Edwin Hubble's subsequent discovery of Cepheids in Andromeda settled the question in Curtis's favour, proving that spiral nebulae were, indeed, distant galaxies. This resolution transformed understanding of the universe's scale and, by extension, the Milky Way's place within it. The opposition, though ultimately resolved against one side, had served its purpose by forcing the question into sharper focus and motivating the observations that provided an answer. In later decades, opposition arose over the methods used to estimate the Milky Way's stellar population. Different approaches produced different results, sometimes varying by factors of 2 or more. Proponents of luminosity function methods argued that statistical sampling of well-studied regions provided the most reliable estimates. Critics pointed out that these samples might not be representative, that the luminosity function might vary across the galaxy, and that uncertainties in the faint end of the distribution introduced large errors. Advocates of mass-based estimates countered that gravitational measurements provided a more robust foundation, less dependent on detecting faint individual stars. Opponents noted that mass-based methods required separating stellar mass from gas and dark matter, introducing their own uncertainties and assumptions. The debate was technical, sometimes arcane, but it mattered because it exposed the weaknesses in each approach and drove improvements in both. Another battleground was the definition of what counted as a star. When brown dwarfs were first discovered in the mid-1990s, they sparked immediate controversy. Were they stars or not? They formed like stars, they had stellar compositions, but they never sustained hydrogen fusion. Some astronomers argued they should be counted in any complete census of the galaxy. Others insisted they were a separate category, neither star nor planet, and should not be included. The debate was partly semantic, but it had practical implications. Including brown dwarfs could add tens or even hundreds of billions to the total count, dramatically changing the answer to the question. Excluding them meant accepting a narrower definition of what constituted a star. The opposition between these views persisted for years, with different studies making different choices and producing correspondingly different estimates. Stellar remnants provoked similar debates. White dwarfs were clearly the corpses of former stars, but they no longer fused hydrogen. Should they be counted? What about neutron stars and black holes? The question of how many stars existed in the galaxy became entangled with the question of how stars should be defined, and different answers to the definition produced different counts. There was also opposition from those who believed the entire enterprise was misguided. A few critics argued that the uncertainties were so large, the assumptions so questionable, and the methods so indirect that any estimate of the Milky Way's stellar population was essentially guesswork. They pointed to the wide range of published values as evidence that astronomers did not really know what they were talking about, that the number was being made up rather than measured. This opposition forced defenders to articulate their methods more clearly, to quantify uncertainties more rigorously, and to explain why a range of possible values was still meaningful. The critics were wrong in suggesting the estimates were baseless, but they were right to demand transparency about limitations. The battle for truth required acknowledging what was known and what was not, what could be measured and what had to be inferred. Some opposition came from outside astronomy. As estimates climbed from millions to billions to hundreds of billions, skeptics in other fields questioned whether such numbers could be trusted. How could astronomers claim to know how many stars filled the galaxy when they could only observe a tiny fraction directly? Was this not hubris, making grand claims based on limited evidence? The response was to explain the logic of statistical inference, the same logic used in fields from epidemiology to ecology. You do not need to count every individual to estimate a total population if your sample is representative. The methods were sound, the uncertainties quantified, the assumptions explicit. The battle was not just for truth but for credibility, convincing skeptics that the estimates, though uncertain, were grounded in real science. Internal opposition also arose over priorities. Some astronomers argued that counting stars was a distraction from more important questions. Why obsess over the total number when we could be studying stellar physics, exoplanets, or galaxy evolution? Resources were finite, telescope time limited. Should surveys aimed at cataloguing faint stars really take priority over other research? The counterargument was that knowing the galaxy's stellar population was foundational. It informed every other question about the Milky Way's structure, history, and future. It provided context for exoplanet searches and estimates of where life might exist. It was not a distraction, but a prerequisite. The opposition on this front was about values and priorities, and it was never fully resolved. Different astronomers continued to pursue different questions based on their own interests and judgments. What united all these forms of opposition was the underlying commitment to truth. The debates were not about personalities or egos, though those sometimes played a role. They were about getting the answer right, or as right as possible given the constraints. The opposition forced continual re-evaluation of methods, assumptions, and interpretations. It prevented complacency and overconfidence. It made the eventual consensus stronger because it had survived scrutiny. The battle for truth is ongoing. New surveys continue to refine estimates. New discoveries, like populations of ultra-faint dwarf galaxies merging with the Milky Way, add complexity. New theoretical insights change how models interpret observations. The opposition has not disappeared. It has evolved, focusing on finer details as the broad outlines have become established. But through all the debates and controversies, a remarkable fact emerges. Despite the opposition, despite the different methods and definitions, despite the uncertainties and limitations, the estimates converge. Nearly all serious studies place the Milky Way's stellar population in the hundreds of billions. The range is wide, but the order of magnitude is clear. The battle for truth has produced not perfect certainty, but robust consensus. And that is perhaps the most important lesson. Science does not require unanimity. It requires honest disagreement, rigorous debate, and a shared commitment to evidence. The opposition, far from being an obstacle, was part of the process that led to understanding. The truth that emerged was stronger for having been challenged, tested, and refined through conflict. There comes a point in the pursuit of any profound question when the accumulation of knowledge reaches a critical mass, when disparate pieces of understanding suddenly coalesce into something larger, when you realize you are not just learning facts but seeing the world differently. For the question of how many stars fill the Milky Way, that awakening came gradually across the late 20th and early 21st centuries, as observations, models, and theories converged into a new awareness of what our galaxy truly was. The awakening was not a single revelation, but a dawning comprehension that unfolded in stages. Each new survey revealed populations that had been invisible before. Each refinement of methods narrowed the range of possibilities. Each comparison with other galaxies provided context. And slowly, the realization emerged that the Milky Way was not just a collection of stars, but a vast, complex, dynamic system containing hundreds of billions of individual suns, each following its own trajectory, each with its own story, all bound together by gravity into a coherent whole that had existed for billions of years and would continue for billions more. The first aspect of the awakening was the sheer abundance. When estimates settled into the hundreds of billions, when that number became robust and widely accepted, it forced a reckoning with what abundance on that scale meant. It was not just that there were many stars, it was that there were so many that the galaxy could be profligate with them, that entire populations could live and die without noticeably affecting the total, that the loss of millions of stars to various processes was statistically insignificant against the backdrop of hundreds of billions. This abundance meant opportunity. If there were hundreds of billions of stars, and if planetary systems were common as observations increasingly suggested, then the galaxy contained not just billions, but trillions of worlds. Among those trillions, the number that fell within, habitable zones where conditions might support life, could number in the billions. Even if the emergence of life was rare, even if intelligence was rarer still, the sheer number of opportunities meant possibilities that previous generations could barely imagine. The awakening brought with it a new awareness of diversity. The Milky Way's stars were not all alike. They ranged from massive blue supergiants burning bright and brief to tiny red dwarfs glowing faintly for trillions of years. They included binary systems where two stars danced around each other, triple systems with complex gravitational interactions, and solitary wanderers like our Sun. They spanned ages from newborn protostars still forming to ancient, population 2 stars nearly as old as the universe itself. This diversity meant that the galaxy was not a monolithic structure but a tapestry woven from countless individual threads. Each star contributed to the whole while remaining distinct. The awakening was realizing that, when we talked about hundreds of billions of stars, we were not talking about identical objects, but about a population as varied as humanity itself, with the difference that the stellar population numbered not billions but hundreds of billions. Another dimension of the awakening involved time. The galaxy's stellar population was not static. It evolved. Stars formed constantly in molecular clouds throughout the disk. Every year, perhaps a few new stars ignited, adding to the total. Other stars died, some quietly fading into white dwarfs, others exploding in supernova that briefly outshone the rest of the galaxy. The balance between birth and death meant the total population changed, though slowly on human timescales. This temporal awareness shifted perspective. The Milky Way was not a fixed catalogue of objects but a living system, constantly recycling matter through cycles of star formation and death. The gas that formed new stars came partly from stars that had died billions of years. ago. The heavy elements in our own bodies were forged in ancient stars that no longer existed. The galaxy had a history, and understanding that history required understanding how the stellar population had changed over time. The awakening also brought awareness of hiddenness. Most of the galaxy's stars were invisible to casual observation. They were too faint, too distant, too obscured by dust. The visible stars, the ones that dominated the night sky and inspired ancient myths, represented only a tiny fraction of the total. The real population lived in shadows, revealed only by patient surveys with sensitive instruments. This realization was humbling. It meant that what we saw was not what was there, that the universe presented an edited version of reality to our senses, that truth required looking beyond appearances. The awakening was understanding that the Milky Way's hundreds of billions of stars were mostly hidden, that our place in the galaxy was among an invisible majority, and that the bright lights we celebrated were exceptions rather than representatives. The awakening brought a new awareness of scale. Hundreds of billions was not just a number. It was a scale that exceeded normal human cognition. It required analogies and comparisons to make it feel real. More stars than all the grains of sand on many beaches. More stars than all the words spoken by all humans in history. More stars than seconds in millions of years. These comparisons helped, but they also highlighted the gap between intellectual understanding and visceral comprehension. The awareness of scale extended beyond the Milky Way. If our galaxy contained hundreds of billions of stars, and if the observable universe contained hundreds of billions of galaxies, then the total number of stars in the cosmos was almost meaningless. Hundreds of sextillions, a number so large that it ceased to communicate anything except vastness itself. The awakening was realizing that our galaxy, enormous as it was, represented only one tiny corner of a universe filled with similar structures, each containing its own hundreds of billions of stars. This cosmic context brought both wonder and vertigo. Wonder at the richness of the universe, at the sheer abundance of matter and energy organized into stars and galaxies. Vertigo at the realization of how small we were, how recent, how peripheral to the grand architecture of the cosmos. The Earth was one planet among perhaps trillions. The Sun was one star among hundreds of billions in the Milky Way, which was one galaxy among hundreds of billions in the observable universe. Yet the awakening was not entirely humbling. It was also empowering, because despite our smallness, despite our brief existence, we had figured this out. We had measured the unmeasurable, counted the uncountable, grasped something of the galaxy's true scale, that capacity for understanding, for asking questions about scales that dwarfed us and then developing methods to answer them, was itself remarkable. The awakening brought awareness not just of our insignificance, but of our capability. The new awareness also touched philosophy and meaning. If the galaxy contained hundreds of billions of stars, what did that imply about life, intelligence, and purpose? Were we alone? Almost certainly not, given the scale. Were we common? That remained unknown, but the opportunities for life were so numerous that it seemed unlikely Earth was unique. Were we significant? Not in the sense of being central or special, but perhaps in the sense of being participants in something vast, observers capable of appreciating the whole. The awakening transformed how we saw the night sky. What had once appeared as a few thousand visible stars was now understood to be a glimpse of hundreds of billions. The Milky Way's pale band was not a simple glow but the combined light of 100 billion suns, most too faint to distinguish individually but collectively creating the luminous river, stretching across the darkness. Every dark patch was not empty but filled with hidden stars, waiting to be revealed by better instruments. This new awareness spread beyond astronomy. It entered popular consciousness through documentaries, books, and science communication. The phrase hundreds of billions of stars became familiar, a shorthand for cosmic scale. It inspired artists, writers, and filmmakers to imagine what such abundance meant for stories of exploration, contact, and meaning. The awakening continues today. Each new survey adds detail to the picture. Each refinement of estimates sharpens understanding. Each discovery of a new stellar population or a new type of star adds complexity. The awareness that began with the simple recognition that the galaxy contained more stars than we could easily count has evolved into a sophisticated understanding of what those stars are, where they are, how they formed, and what their existence means for everything else. The awakening is not complete. It may never be complete, but it represents a fundamental shift in how we understand our place in the universe. We are surrounded by abundance. We live among hundreds of billions of companions, most invisible, most unknown, but all part of the same galactic family. That awareness changes us, opens possibilities, and reminds us that the universe is richer than we can fully grasp, but not richer than we can partially understand. At the heart of every great question lies a revelation, a moment or realization when the answer ceases to be mere information and becomes something deeper, something that touches not just the mind, but the sense of wonder and connection to the cosmos. For the question of how many stars fill the Milky Way, the revelation is not simply that the number is large, but what that number reveals about existence itself, about possibility, about our place among an almost incomprehensible multitude of other suns. The deepest truth is this: we are not alone in the prosperous sense of isolation. We are surrounded. Every direction we look, stretched across the great disk of the Milky Way, scattered through its central bulge, drifting in its outer halo, there are stars, hundreds of billions of them, each one a sun, each one potentially hosting worlds, each one burning with the same physics that governs our own star, each one a point of light in the darkness. This revelation shifts something fundamental in how we see ourselves. For most of human history, the visible stars were few enough to count, at least in principle. A few thousand points of light scattered across the sky. The universe felt finite, bounded, knowable. But the revelation that the galaxy contains hundreds of billions of stars, most of them invisible, transforms that sense of finitude into something approaching infinity. We live in a galaxy so full of stars that new suns are born every day, and old ones die, and the total barely changes. We inhabit a structure so vast that light takes 100,000 years to cross it. So crowded that in some regions stars are separated by distances smaller than the space between planets in our solar system. So enduring that it has persisted for 13 billion years and will continue for billions more. The revelation is about scale, but it is also about potential. If there are hundreds of billions of stars, then there are likely hundreds of billions of planetary systems. Estimates from exoplanet surveys suggest that most stars have at least one planet. That means the Milky Way could contain not billions but trillions of worlds. Among those trillions, a significant fraction will fall in habitable zones, where temperatures allow liquid water, the essential ingredient for life as we know it. Even conservative estimates suggest billions of potentially habitable worlds in the galaxy. Billions of places where chemistry could become biology, where simple organisms could evolve into complex ones, where intelligence might emerge and ask the same questions we ask, looking up at their own night sky and wondering how many companions they have in the darkness. The revelation is that the question of whether we are alone in the universe is not a question about possibility, but about probability. With hundreds of billions of stars and potentially billions of habitable worlds, life elsewhere seems not just possible, but likely. The universe is not barren. It is, almost certainly, alive in ways and places we have not yet discovered, populated by organisms we cannot yet imagine, shaped by evolutionary paths that may converge with ours or diverge into something utterly alien. This does not mean we will find life easily or soon. The galaxy is so vast that even if life is common, the distances between living worlds could be enormous. Two civilizations could exist simultaneously, both gazing at the stars, both wondering if they are alone, and never know about each other because the signals they send are lost in the noise of space or arrive, too late or too early to be detected. The Milky Way could be full of life and still feel empty to any individual species looking for neighbors, but the potential is there. The opportunity exists. The sheer number of stars ensures that even if the odds of life are low, the absolute numbers could be high. If only 1 in a million stars hosts a world with life, that still means hundreds of thousands of living worlds. If only 1 in a million of those develops intelligence, that still means hundreds or thousands of civilizations. The revelation is that the galaxy is a place of abundance, where rarity on a per-star basis does not translate to rarity in absolute terms. Another layer of the revelation involves time. The stars we see, the 100 billion or 400 billion suns scattered across the Milky Way, are a snapshot of a single moment in galactic history. But the galaxy has a past and a future. Over its 13 billion year history, it has formed far more stars than currently. To exist, many have already died, leaving behind white dwarfs, neutron stars, or black holes. If we count all the stars that ever existed in the Milky Way, the total could be several times higher than the current population. This temporal dimension means that the galaxy is not just full of stars but full of histories. Every white dwarf is the remnant of a star that once shone, perhaps hosting planets, perhaps nurturing life. Every nebula, glowing in the light of newborn stars, is a place where future worlds will form. The revelation is that the galaxy is not static, but alive in the sense that it evolves, changes, renews itself through cycles of birth and death that have repeated for eons and will continue for eons to come. The deepest truth also touches on connection. The atoms in our bodies were forged in stars that died before the sun was born. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were created in stellar furnaces and scattered into space by supernova explosions. We are not separate from the stars. We are made of them. We are, in Carl Sagan's famous phrase, star stuff, contemplating stars, matter organized by the universe into patterns complex enough to ask questions about their own origins. This connection is not metaphorical, it is literal. The hundreds of billions of stars in the Milky Way are not distant, unrelated objects. They are part of the same system that produced us, linked through the cycles of matter that build stars, planets, and living beings. Every star we see, every star we cannot see, is part of our extended family, sharing the same galactic home, made of the same fundamental particles, governed by the same physical laws. The revelation brings both awe and comfort. Awe at the sheer scale, at the recognition that we are part of something so vast it exceeds our ability to fully grasp it. Comfort in knowing that we are not isolated, not alone even in the absence of contact with other life, because we are, surrounded by hundreds of billions of other suns, each one a companion in the darkness, each one contributing to the great spiral structure we call home. The deepest truth is that the Milky Way is not just a galaxy, it is our context, our neighborhood, the the stage on which our entire history has played out and on which all our possible futures will unfold. Understanding that it contains hundreds of billions of stars is not just knowing a number. It is understanding that we exist within abundance, that opportunity surrounds us, that the universe is not sparse but rich, not empty but full. This revelation does not answer all questions. It raises new ones. What is life like on worlds orbiting red dwarfs, the most common stars? How many civilizations have risen and fallen in the galaxy's long history? What will become of the stellar population as the Milky Way ages, as star formation slows, as the galaxy eventually merges with Andromeda to form something new? The revelation opens doors rather than closing them, inviting exploration and wonder rather than providing final answers. But what it does provide is perspective, a sense of place in the cosmos, an understanding that we are part of something immense, ancient, and enduring. The revelation is that the question of how many stars fill our galaxy is ultimately a question about home, about where we come from and what surrounds us, about context and connection, and the deep truth that we are citizens of a galaxy containing more suns than we can count, more possibilities than we can imagine, more wonder than we can ever exhaust. After the facts have been gathered, after the estimates have been refined, after the revelation has settled into understanding, there comes a time for reflection, a moment to step back from the technical details and ponder what it all means, not just for astronomy, but for how we see ourselves, how we understand our existence, and what questions we carry forward into the future. The Milky Way contains hundreds of billions of stars. That number, once merely a fact, now resonates with implications that touch every aspect of human thought. What does it mean to live in a galaxy so vast? What does it mean to be one civilization, if we are indeed civilized, among potentially many others? What does it mean to gaze up at a night sky and know that most of what fills it is invisible to our eyes, but nonetheless real and abundant? One reflection centers on humility. The history of astronomy has been a story of displacement, of realizing again and again that we are not as central or as special as we once believed. The Earth is not the center of the solar system. The solar system is not the center of the galaxy. The galaxy is not the center of the universe, which has no center at all. And now we know that the Sun, our home star, is one among hundreds of billions, ordinary in almost every respect. This humility could feel diminishing. It could make human life seem insignificant, our concerns trivial, our existence a brief flicker in an uncaring cosmos. And sometimes, in moments of existential contemplation, it does feel that way. But there is another way to understand it. Humility is not the same as meaninglessness. To recognize that we are small is not to say we are unimportant. It is to say we are part of something larger, connected to a cosmos that contains more than we can fully comprehend. The reflection brings perspective. When we worry about daily concerns, when we become consumed by immediate problems, it can help to remember that we live on one planet, orbiting one ordinary star among hundreds of billions, in a galaxy that is itself one among hundreds of billions. That perspective does not make our concerns disappear. Suffering is still suffering, joy is still joy, regardless of scale, but it provides context, a reminder that our moment in time and space is both precious and fleeting, worth appreciating precisely because it is limited. Another reflection, to involve possibility. If the Milky Way contains hundreds of billions of stars and potentially billions of habitable worlds, then the galaxy is full of places where life might exist, where intelligence might have emerged, where civilizations could have risen and fallen, or could be flourishing even now. We do not know. We have not found them yet. but the sheer abundance of opportunities makes it seem unlikely that Earth is unique. This possibility changes how we think about ourselves. If we are not alone, if intelligence is common in the galaxy, then our perspective is parochial, shaped by the accident of living on one particular world in one particular time. Other intelligences, if they exist, will have their own perspectives, their own questions, their own ways of understanding the universe. Meeting them, if we ever do, would be among the most transformative events in human history, forcing us to see ourselves through alien eyes and to recognize that our way of being is one among many. But even if we are alone, if life is so rare that Earth represents a statistical fluke in a galaxy of hundreds of billions of stars, that would be equally profound. It would mean that consciousness, the ability to ask questions and seek answers, is extraordinarily precious, perhaps unique to our planet. In that case, we bear a responsibility not just to ourselves but to the cosmos, to preserve and nurture the only place where the universe has become aware of itself. The reflection leads to questions about legacy. What will we leave behind? Will humanity endure long enough to spread beyond Earth, to become a multi-world species, to add our own chapter to the galaxy's story? Or will we be a brief episode, a species that arose, flourished for a geological instant, and vanished, leaving behind no trace visible from the stars? Stars have been forming, living, and dying throughout that immense span. Billions of years from now, the 24 galaxy will still be here, though changed. The Sun will have become a white dwarf. The Milky Way will have merged with Andromeda. New generations of stars will burn in regions that are now empty space, but the galaxy itself will endure. Against that timescale, human existence is almost invisibly brief. Our entire history, from the first hominids to the present day, spans perhaps a few million years. The oldest human civilizations are only a few thousand years old. If the galaxy's history were compressed into a single year, humanity would exist for a fraction of the last second. We are newcomers, recent arrivals on a stage that has hosted countless stellar dramas long before we existed. And yet, we are here. We are capable of asking these questions, of measuring the galaxy, of understanding something of its scale and structure. That capability, however recent it may be in cosmic terms, is meaningful. It represents the universe becoming aware of itself, matter organizing into patterns that can contemplate their own existence. That is not nothing. It is, perhaps, among the most remarkable phenomena in the cosmos. The reflection also touches on connection. We are not isolated individuals on a lonely planet. We are part of a continuum that stretches back through time to the formation of the galaxy, back further to the Big Bang itself. The atoms in our bodies were forged in stars. The energy that powers our lives comes from the sun, itself a typical star among hundreds of billions. The elements in the earth, the air we breathe, the water we drink, all pass through stellar furnaces before becoming the material of our world. This connection means that the galaxy's hundreds of billions of stars are not distant, irrelevant objects. They are part of the system that made us possible. We exist because stars existed first, because they fused hydrogen into heavier elements, because they exploded and scattered those elements into space, because the enriched gas eventually collapsed into new stars and planets, including our own. We are the descendants of stars, the offspring of the galaxy itself. Reflecting on this brings a sense of belonging. The Milky Way is not a cold, indifferent void filled with distant suns. It is our home, our origin, the context in which everything we know has unfolded. The hundreds of billions of stars are our neighbours, our companions, the extended family of lights that share this galactic space with us. The reflection also invites wonder. Despite all we have learned, despite all the surveys and models and estimates, the galaxy remains mysterious. We know it contains hundreds of billions of stars, but we have only catalogued a tiny fraction. We know many of those stars have planets, but we have only confirmed a few thousand. We know that the conditions for life exist on billions of worlds, but we have only found life on one. There is so much left to discover, so many stars to catalogue, so many planets to characterize, so many questions about how the galaxy formed and how it will evolve. The reflection on meaning is not a conclusion but an opening, an invitation to continue exploring, to keep asking questions, to remain curious about the cosmos we inhabit. In the end, pondering the meaning of the Milky Way's stellar population brings us back to ourselves. We are the ones asking the question. We are the ones marveling at the scale. We are the ones trying to make sense of hundreds of billions of stars and what that means for existence, for possibility, for purpose. The meaning is not inherent in the stars themselves. They burn and shine indifferent to our interpretations. The meaning is what we bring to them, the significance we find in understanding our place among them, the questions we ask and the wonder we feel when contemplating their abundance. The Milky Way contains hundreds of billions of stars. That is a fact. But what it means is a reflection, an ongoing contemplation that each generation will approach in its own way, finding new insights, new connections, new reasons to look up at the night sky in awe. Every journey must end, even a journey through a question as vast as how many stars fill our galaxy. We have travelled together through history and method, through discovery and debate, through revelation and reflection. And now, as this exploration draws to a close, we return to where we began, standing beneath the night sky, looking up at the Milky Way's pale band, knowing more than we did, but still surrounded by mystery. The legacy of this question is not a single number. The legacy is the journey itself, the centuries of effort that brought us from wondering about a few thousand visible stars to understanding that we live among hundreds of billions. The legacy is the telescopes built, the surveys conducted, the data analysed, the models refined, the debates resolved. It is the accumulation of human curiosity and ingenuity applied to a question that seemed impossible but proved answerable, at least within limits. We know now that the Milky Way contains somewhere between 100 billion and 400 billion stars. That range is wide, spanning hundreds of billions, but it represents an extraordinary achievement. We cannot count every star individually. Most are too faint, too distant, too obscured, but we can estimate, we can model, we can infer, and those estimates converge on a scale that transforms how we understand our place in the cosmos. The legacy is also in what comes next. The question of how many stars fill the galaxy has opened countless other questions. How many of those stars have planets? How many planets are habitable? How many harbour life? Is intelligence common or rare? Are we alone or surrounded by civilizations we have not yet detected? Each question builds on the foundation of understanding the stellar population, and each invites new exploration. Future generations will continue refining the estimate. New telescopes will reveal fainter stars. New surveys will map the galaxy in greater detail. New methods will account for populations we have not yet fully characterized. The number will shift, the range will narrow, but the fundamental truth will remain. We live in a galaxy of extraordinary abundance, surrounded by more suns than we can easily count. The legacy extends beyond astronomy. It touches philosophy, culture, and the arts. The knowledge that hundreds of billions of stars fill our galaxy has entered the collective imagination, shaping how we tell stories, how we think about the future, how we understand ourselves. Science fiction explores the possibilities of that abundance, imagining civilizations on worlds orbiting distant suns. Philosophical discussions ponder what it means to exist in such a vast and crowded universe. Artists capture the wonder of the night sky, knowing that what we see is only the beginning of what exists. The return is to simplicity. After all the technical detail, after all the methods and debates, we come back to the fundamental experience of looking up at the stars. That experience has not changed in essence since humans first gazed at the night sky thousands of years ago. The stars still shine. The Milky Way still stretches across the darkness. The sense of wonder and insignificance, of connection and mystery remains. But now, when we look up, we see differently. We know that each visible star represents millions of invisible ones. We know that the pale glow of the Milky Way is the combined light of 100 billion suns or more. We know that we are looking at a structure so vast that light takes 100,000 years to cross it, so ancient that it formed when the universe was only 1 billion years old, so dynamic that stars are being born and dying even as we watch. That knowledge does not diminish the wonder, it deepens it. The night sky becomes richer, layered with understanding that makes each point of light more meaningful. The stars are not just pretty lights. They are suns, each one potentially hosting worlds, each one part of the same galactic family we belong to, each one contributing to the immense structure we are privileged to observe from within. The return is also to humility. We have answered the question as well as we can, but we acknowledge the limitations. The exact number remains uncertain. The definitions are debatable. The methods have margins of error. We will never have perfect knowledge, and that is acceptable. The universe does not owe us certainty. It is enough to have approximate understanding, to know the scale even if we cannot pin down every detail. This humility is not defeat. It is wisdom. It recognizes that some questions are so large they cannot be fully answered, that some truths are approached asymptotically, getting closer and closer but never quite reaching perfect precision. The question of how many stars fill the Milky Way is one such question, and the journey toward answering it is more important than arriving at a final number that will never quite be final. We leave behind knowledge for those who come after, and we return to the same sense of wonder that motivated the question in the first place. Every generation will ask this question anew, will use the tools of their time to refine the answer, will contribute their piece to the ongoing exploration, and every generation will stand beneath the same night sky, looking up at the same stars, feeling the same mixture of smallness and connection that makes the question worth asking. As this journey ends, let yourself float gently back to wherever you are listening from tonight. Perhaps you are in bed, ready to drift into sleep. Perhaps you are in a chair, letting your thoughts wander. Perhaps you are outside, looking up at the real sky, seeing the stars with new understanding. Wherever you are, know that above you, around you, stretching across the vast disk of the Milky Way, there are hundreds of billions of stars. Most you will never see. Most are too faint, too distant, too hidden, but they are there, burning quietly in the darkness, orbiting the galactic center on timescales measured in hundreds of millions of years, forming in clouds of gas, living for millions or billions or trillions of years, dying and leaving behind remnants that mark their passage. Each one a sun, each one a world unto itself, and you are here, on one planet, orbiting one of those stars, part of a system that contains more companions than you can count. You are surrounded by an abundance of light, most of it invisible, but all of it real. The galaxy is full, richer than imagination, more crowded than comprehension. The question of how many stars fill the Milky Way began as a simple wonder and became a scientific pursuit that spanned centuries. It has been answered, not with perfect precision, but with sufficient clarity. Hundreds of billions. That is the legacy we have received and the knowledge we pass forward. That is the truth we return to, again and again, whenever we look up at the night sky and ask the question that never truly goes away. How many stars are in our galaxy? Hundreds of billions. More than we can count. More than we need to count. Enough to fill the darkness with light, to populate the void with possibility, to remind us that we are part of something vast and ancient and enduring. Thank you for traveling with me through this question, through this journey from ignorance to understanding, from wonder to knowledge, and back to wonder again. If you found peace in this exploration, if the gentle drift through galactic scales brought you calm, then the journey has served its purpose. You can return here anytime the question calls to you, whenever you want to float again through the quiet spaces between the stars, whenever you need reminding that we live among hundreds of billions of companions in the darkness. Until then, rest well beneath your own small piece of sky. The stars are there, whether you can see them or not, and they will be there tomorrow, and 1,000 years from tomorrow, burning steadily in the night. Safe travels through the cosmos of your dreams.